Hello there, and welcome back to The Sleepy Science. You're standing at the edge of a tall cliff, not metaphorically, but quite literally, somewhere windswept and a little too chilly for your comfort. You can feel the air pressing against your skin, thick with anticipation. Below, nothing but a blur of greens and greys. Above, an expanse so wide it almost swallows you. Your toes curl slightly over the edge. This question mark. This is how flight begins. Not with wings or engines or sleek chrome fuselages, but with falling. Terrifying, unstoppable, wonderfully inefficient falling. And honestly, you probably won't survive this if you try it without some serious upgrades. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your current location and local time in the comments, especially if you're listening from somewhere airborne. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You step back from the edge, but not too far. Falling, it turns out, is the foundation of flight. You don't so much beat gravity as you negotiate with it, tactfully, precisely, and with a lot of math. Think of gravity as that slightly overbearing friend who refuses to let you leave the party early. You can't fight it directly, but you can sidestep, dance around, and with the right physics, convince it to let you rise. At first glance, flying seems like pure rebellion. You're floating, lifting, zooming, defying the very rules that keep apples falling and ankles spraining. But take a closer look and it becomes clear. Flight isn't about disobedience, it's about harmony. Your wings, or rotors, or thrusters, or conveniently placed feathers don't fight gravity. They partner with it, like a slightly dysfunctional but ultimately loyal relationship. Isaac Newton would have called it an equal and opposite reaction kind of thing. He never flew anything, of course, unless you count tossing an apple across the yard. Still, his third law underpins every takeoff. Push air down, and you go up. You're not escaping gravity, you're just redirecting the conversation. But long before we understood the physics, or even had words like lift or drag, humans watched birds with a deep and dangerous envy. We built wings out of wood, silk, wax. We jumped off castles. Some of us even flapped furiously, convinced that all we needed was enthusiasm. Gravity had a good laugh. It always wins, unless you've done your homework. Which brings us back to the cliff, and that tight feeling in your stomach. You shift your weight from heel to toe and try to calculate the odds. You've got nothing but a robe stitched with goose feathers and an optimistic pamphlet titled "You Too Can Soar." Trust me, it's not going to end well. Still, this is where the story begins. Not with triumph, but with splat. With trial, error, and humbling lessons. Because for most of history, flying wasn't a smooth ascent. It was a painful, often hilarious descent. The physics were always there, we just hadn't cracked the code yet. Some of the earliest human attempts at flight were less science and more enthusiastic guessing. Abbas ibn Firnas, a 9th century Andalusian polymath, allegedly tried gliding with wings made of silk and wood. He survived, barely, and later admitted he forgot to account for how to land. Historians still argue whether he really flew or just plummeted stylishly. It wasn't until the Renaissance that things got slightly less ridiculous. Leonardo da Vinci, artist and noodler of impossible machines, filled notebooks with ornithopters, devices that flapped like birds, and spiral air screws that hinted at helicopters centuries ahead of their time. Of course, none of them flew, but the ideas, they mattered. He was one of the first to suggest that flying wasn't about flapping like a chicken having an existential crisis. It was about understanding the rules of air. You imagine Leonardo squinting at a bird, muttering to himself, and sketching what looks suspiciously like a pasta strainer with the wings. Sure, it wouldn't get off the ground, but in his doodles, the first blueprints of aviation quietly took shape. Let's be honest, flying is unnatural for humans. We're built for walking, maybe climbing, and, if absolutely necessary, awkward swimming. Our bones are dense, our muscles are in the wrong places, and we don't come pre-installed with feathers. But we do come equipped with curiosity, and that's what makes the impossible seem like just another group project. Even animals have to play by gravity's rules. Flying squirrels don't really fly, they glide, and not always gracefully. Chickens are technically birds, but they'd rather not be reminded. Evolution too is a compromise between ambition and practicality. The physics of flight, lift, drag, thrust, weight, aren't just mechanical, they're biological. They shaped the hollow bones of pigeons, the high-aspect wings of albatrosses, and the baffling flight muscles of hummingbirds that beat over 50 times per second. Now, let's take a brief side trip to somewhere weirder. In 18th century France, a group of fashionable nobles held flying salons where they'd try on glider capes in ornate ballrooms and fling themselves off staircases. It was the original cosplay disaster. They called it le jeu aérien, the aerial game. It was less about physics and more about pageantry, but it proved one thing. People were desperate to leave the ground, no matter how ridiculous they looked doing it. All of this fumbling, falling, and failed flapping paved the runway for something smarter. The idea that to fly, you don't mimic birds, you understand air. The invisible sea you move through isn't passive. It pushes, pulls, and swirls. Every gust is a negotiation. Every liftoff a physics exam. You either pass or dramatically fail. And here's the truth most textbooks avoid. The sky doesn't want you. It doesn't care if you flap harder or dream bigger. It is indifferent, and gravity is downright petty. But with enough patience, a bit of clever math, and some very expensive aluminum, you can convince them both to let you rise. So next time you're on a plane, sipping lukewarm ginger ale at 30,000 feet, remember this. Flight isn't magic. It's physics wearing a cape. And it all started with one very human question. What if we didn't have to fall? The air around you feels still, but it never really is. Even in the quietest moment, molecules are zipping past your skin, bouncing off your face like invisible ping-pong balls. You don't see them, but you absolutely feel them, especially when you try to move through them too fast. And that's the thing, the sky isn't empty. It's not some vast, empty nothing waiting to be conquered. It's a crowded ballroom full of pushy dancers, and every aircraft, no matter how sleek or powerful, has to elbow its way through. Air, annoyingly enough, has weight. Not a lot, but enough to make a difference. A single cubic metre of air at sea level weighs about 1.2 kilograms. Multiply that by the space around a plane in flight, and suddenly you're dragging a pretty hefty invisible blanket everywhere you go. That blanket has texture, temperature, and resistance. It can help you or it can ruin your day. It all depends on how you treat it. You take a slow, deep breath, and imagine what's inside it. Oxygen and nitrogen mostly, with a dash of argon and the occasional scandalous whiff of carbon dioxide. But more importantly, air has pressure. Every square inch of your body is under about 14.7 pounds of it at sea level. You're basically being hugged by a very persistent atmospheric bear at all times. This pressure drops as you rise, which is why ears pop on airplanes and why mountaintops make your lungs feel like they're on strike. Here's where it gets even stranger. The way air behaves changes depending on its temperature, humidity, and altitude. Warm air is lighter than cold air. Moist air is lighter than dry air. So yes, a hot, humid summer day in Florida might feel heavy to you, but to a plane, it's practically a feather pillow. Pilots refer to this as density altitude, and it's one of those phrases that sounds made up until you realize it can make or break a takeoff. This brings us to the problem of viscosity. Not the kind in your maple syrup, but close. Air has its own stickiness, a subtle resistance to flow. You don't notice it while walking unless you're sprinting into a headwind or trying to ride a bike with an umbrella. But at high speeds, even the air's slight reluctance to move becomes a serious factor. Pilots and engineers call this aerodynamic drag, and it's basically air's way of saying, no thanks, not today. Historians still argue whether ancient inventors understood air as a fluid or simply saw it as a convenient emptiness to leap into. The Greeks toyed with pneumatics, early studies of air pressure, but didn't quite grasp how it flowed around objects. It wasn't until the 18th century that Swiss physicist Daniel Bernoulli described how fast-moving fluids exert less pressure than slow-moving ones. You'll hear more about him in a moment, but for now just know that his theory turned the whole concept of air from nuisance to opportunity. You stand still again, imagining yourself not as a person, but as a shape in a wind tunnel. As air hits you, it splits, flows around your contours, and rejoins behind you, or doesn't. That separation, that little messy wake behind your back is called turbulence. It's like you left your own messy air signature behind, and the faster you go, The bigger the mess. This is where the idea of streamlining enters the chat. Birds figured it out long before Boeing did. Smooth feathers, tapered tails, narrow beaks. They're all about reducing air disturbance. When engineers talk about laminar flow, they mean air that slides like silk over a surface. Turbulent flow, on the other hand, is more like throwing spaghetti into a box fan. You want less of that. Here's a deliciously weird detour. In the 1930s, some early aerodynamicists conducted tests using cigars and shaving cream. Why? Because cigars produced a steady stream of smoke when puffed, and shaving cream let you trace airflow over small surfaces. They even used cats with bits of tinfoil glued to them to study drag, although the ethics of feline aerodynamics have since evolved, thankfully. As for practical applications, consider the humble paper airplane. Fold a sheet of notebook paper into a dart and toss it across the room. Congratulations, you've just conducted a hands-on experiment in airflow. If it glides well, you've managed a decent balance of lift and drag. If it nosedives into your cat's water dish, well, welcome to the club. The point is, even that simple toss involves complex interactions between pressure zones, airflow direction, and your own poorly folded intentions. What's fascinating is how every creature that flies must learn to read the air. Birds, bats, bees, they all rely on feedback loops that sense minute changes in pressure and direction. Some birds can even detect differences in air density with their beaks. Falcons, for example, tuck their wings into a bullet shape to slice through air at speeds that could strip paint off a barn. But they only do it because they've mastered the currents, rising thermals, ridge lifts, wind shadows. It's less flying and more surfing, but with talons. Human-made flyers have to learn the same language. Pilots train for years to sense the subtleties of headwinds, crosswinds, updrafts, and tailwinds. The air isn't just background, it's the main character, and it never sits still. That's why no two flights are exactly the same. Even with autopilot engaged, the aircraft is constantly whispering with the sky, negotiating tiny changes, correcting courses, smoothing out jitters. Some engineers still debate whether we fully understand how air interacts with complex surfaces at extreme speeds. Supersonic flow, shock waves, boundary layer separation. These are turbulent territories, literally and metaphorically. Even with wind tunnels and computer models, some flight behaviours only become clear once you test them in real-world skies. It's humbling to realise that the atmosphere still keeps a few secrets. So the next time you look up at a plane carving its path across the blue, remember, it's not slicing through emptiness. It's swimming through a thick, shifting ocean of gas molecules. Every wingtip vortex, every contrail, every tiny bounce of turbulence is a sign of the sky pushing back. And that's not a bug, it's a feature. Because without that invisible resistance, flight wouldn't just be difficult, it would be impossible. You settle in, imagining yourself floating mid-air completely still while a river of atmosphere rushes past. You're not just suspended in nothingness, you're balanced in a vast invisible stream, and every moment in the sky is a quiet conversation with the air itself. You're not just drifting anymore, you're flying, in theory. And the reason you're still up here isn't luck or magic or a prayer to the sky gods, though, let's be honest, those never hurt. No, it's because 4 distinct forces are working overtime to keep you from plummeting dramatically back to Earth. You picture them like housemates who didn't choose each other, but now they're stuck splitting the rent on every single flight. They bicker, they balance, they cancel each other out just enough for the miracle of flight to happen. Their names: lift, weight, thrust, and drag. The Fantastic Four of the sky. Or if you're in a less charitable mood, the dysfunctional band that never quite agrees on tempo, but still manages to sell out stadiums. First up, Lift, the drama queen, always trying to go up, always insisting on taking the stairs when everyone else wants the elevator. Lift is the force that pushes your aircraft upward, perpendicular to the direction of oncoming air. It's generated by the wings, more specifically by the shape of the wing and the way air flows around it. We'll give it a whole spotlight in the next section, don't worry. Just know for now that lift has one job: oppose weight. Weight, of course, is gravity's bestie. It's the downer of the group, literally. Weight pulls everything toward Earth, relentlessly, endlessly, without even asking if you're having a good time. It's calculated as mass times gravitational acceleration. In simpler terms, how much stuff you've packed and how hard Earth is tugging on that stuff. wings and engines can try their hardest. But if you overload your aircraft with 5 suitcases of duty-free chocolate, weight is going to have a very stern word with you. Now, meet thrust. Thrust is the motivator, the caffeinated friend who says let's go before anyone else is even out of bed. It's the force that propels your plane forward, usually generated by propellers, jet engines, or the occasional hamster on a treadmill. Early prototypes don't ask. Thrust has one job: to overcome drag. Ah yes, drag, the killjoy, the sky's version of molasses. It's the resistance caused by air molecules slamming into the aircraft as it tries to move. Drag is always there, always whispering slow down in the ear of every pilot. It doesn't care about your itinerary or your dreams of making it to your cousin's wedding on time. Drag only wants to stop you. Now here's where things get complicated. These 4 forces are in constant tug of war, and if even one of them overpowers the others, things get weird fast. Too much lift, you stall. Not enough thrust, you can't even leave the runway. Too much drag, you waste fuel and start flying like a brick in slow motion. Too much weight? Well, then you're not flying, you're falling, with a lot of baggage fees. Historians still argue whether Sir George Cayley, the 19th century British engineer often called the father of aerodynamics, was the first to clearly outline these 4 forces. In a letter dated 1809, he described the basic structure of a flying machine with separate systems for lift, propulsion, and control, basically inventing the airplane on paper long before the Wright brothers built one. He even launched a glider with his coachman as the test pilot. The coachman reportedly resigned immediately afterward. Can't imagine why. Each of these forces has a direction. That's crucial. Lift acts upward, weight pulls downward, thrust moves forward, and drag pulls backward. And for level, unaccelerated flight, say cruising peacefully at 30,000 feet while you sip orange juice from a plastic cup, those forces have to be in perfect balance. Lift equals weight, thrust equals drag. It's like a seesaw that somehow floats in the sky. Of course, flight isn't always level and unaccelerated. Planes climb, descend, turn, and bank. They maneuver through storms and navigate mountain ranges, and sometimes just try to find a runway that isn't temporarily occupied by a moose. This happens more often than you'd expect in Alaska. In those moments, the balance shifts. Pilots adjust throttle, change the angle of the wings, and fine-tune their path through the air to maintain control. It's an intricate ballet of force and counterforce, performed thousands of times a day all around the globe. A fun little side note. In the 1920s, a Hungarian engineer named Theodor von Karman developed a concept called the Karman line, which today defines the boundary between Earth's atmosphere and space, about 100 kilometers up. Above that, the air is so thin that flight, as we know it, just doesn't work. There's not enough air for lift or drag to do their thing. Up there, you're out of the band. It's just you, the void, and Newton's laws trying not to spiral into the abyss. Even on Earth, the balance is delicate. A small Cessna plane flying low over a warm runway has different force interactions than a cargo jet roaring across the Atlantic. Atmospheric pressure, air temperature, altitude, humidity. Every environmental variable changes the math. Pilots learn to think in terms of performance envelopes, the acceptable ranges of speed, weight, and altitude for safe operation. Step outside that envelope, and suddenly your aircraft stops behaving like a plane and starts acting like an expensive paperweight. It's easy to forget when looking at the clean sweep of a wing or the powerful growl of an engine that flight is really just the art of compromise. Every design decision, bigger wings, smaller engines, lighter materials, favours one force over another. Some modern fighter jets, like the F-22 Raptor, are intentionally designed to be aerodynamically unstable, so they can manoeuvre better at high speeds. The computer has to constantly correct their flight path to keep them from doing a very expensive somersault. It's thrilling. It's terrifying. It's physics turned up to 11. There's even debate among scientists and engineers about how exactly these forces interact at micro levels. Boundary layers, turbulent flow, compressibility effects, all are areas where our understanding is still evolving. Despite all our advances, flight remains partly mysterious. Like trying to explain love using only algebra, you can get close to the truth, but never quite hold all of it at once. Still, you don't need to master the equations to feel the magic. Next time you're taxiing down the runway and the engines surge, just close your eyes and listen. That deep vibration under your seat? That's thrust clocking in for work. The lift nudging you into the air? That's Bernoulli and Newton arguing over who deserves more credit. And the drag rattling your tray table just slightly, that's the sky reminding you it's not done playing rough. And you're along for the ride, suspended in a delicate truce between four forces that would rather be anywhere else but somehow, for just long enough, agree to get you there. So now you're gliding smoothly, the forces balance for the moment. But let's take a moment to give some overdue attention to the most glamorous of the group, Lift, the darling of aerodynamics, the misunderstood celebrity. The reason birds get to be smug and paper planes sometimes defy all expectations. Lift gets all the credit for flight, and sure, that's a little unfair to thrust and drag, but we're playing favourites tonight, and Lift deserves the spotlight. You picture yourself standing on a breezy hill, arms stretched out like wings. You tilt them slightly upward, and there it is, that invisible push from below. It's not much, just a nudge really, but it's there. That's Lift teasing you. The dream of rising off the ground begins with that subtle difference in air pressure, that whisper of possibility. Now, the classic explanation, and the one most people hear in school, is Bernoulli's principle. Daniel Bernoulli, the 18th century Swiss physicist, figured out that faster moving fluids exert lower pressure. So when air splits to go over and under a curved wing, it moves faster over the top, reducing pressure there. The slower air under the wing has higher pressure, pushing upward. Voila, Lift. It's elegant. It's taught in every science classroom with a diagram of a wing and a few friendly arrows. But, and here's where it gets spicy, some physicists argue that this isn't the whole story. They point out that Bernoulli's equation alone doesn't account for the actual trajectory of the air, or why it chooses to move faster over the top. Some prefer Newton's third law. Air is deflected downward by the wing, so the wing gets pushed upward in return. Others invoke circulation theory, boundary layer effects, or even vortex dynamics. Historians still argue whether Bernoulli or Newton has the stronger claim to explaining Lift. It's a long-standing debate, filled with whiteboards, passionate hand gestures, and a few well-meaning but deeply confused first-year students. In truth, both principles are right. The wing's shape, angle, and movement all contribute. It's less about one explanation, and more about a stack of them, layered like a very nerdy cake. The shape of a wing, what's called an airfoil, is specially designed to maximize lift while minimizing drag. It's usually curved on top and flatter underneath, which helps airflow faster above than below. But even symmetrical airfoils can generate lift depending on the angle of attack or the angle between the wing and the oncoming air. Too low and you don't get enough lift. Too high and you stall. It's like seasoning. Just the right amount brings everything together. Too much and you ruin Thanksgiving. Lift isn't just about up and down, it's about precision. Every airplane, from a hang glider to a jumbo jet, is designed to maximize lift for its purpose. Gliders have long, narrow wings that stretch toward the clouds like arms begging for a breeze. Fighter jets have short, swept wings made for speed and sudden movement. And birds are absolute geniuses of wing design. Owls have wide, soft-edged wings for silent flight. Swifts and falcons have tapered shapes for high-speed dives. Hummingbirds flap their wings in figure eights, creating lift on both the upstroke and the downstroke, basically showing off. Here's a little-known delight. In World War II, engineers studied seagulls to design better carrier-based aircraft. Seagulls can land on narrow posts in high winds, thanks to their ability to precisely modulate lift with tiny feather adjustments. So yes, your grandfather's fighter plane may have borrowed ideas from that annoying bird who stole your french fries at the beach. Lift also explains why spoilers and flaps are so important on planes. Spoilers reduce lift when you're trying to land, letting the aircraft settle firmly onto the runway. Flaps increase the curvature of the wing, generating more lift at lower speeds. Perfect for takeoff and landing. They're like little aeronautic cheat codes. Press here for more lift. Press again to slow things down. Then there's ground effect, one of aviation's weirder tricks. As a plane gets very close to the ground, like within one wingspan, airflow beneath the wing becomes compressed, increasing lift and reducing drag. This makes landings feel floaty, like the plane is hesitant to touch down. Pilots often describe it as if the plane is skating on a cushion of air, which sounds lovely until you overshoot the runway, because your aircraft suddenly got ideas about staying airborne forever. Lift isn't just for airplanes. Helicopters generate lift by spinning rotor blades that act like wings in motion. Even race cars use inverted airfoils, called spoilers, to generate downforce, which is just lift in reverse. The goal there is to glue the car to the road so it can turn at high speeds without flying off like a very determined frisbee. Insects, of course, break all the rules. A bee's flight once baffled scientists because its wings seemed too small to generate lift for its body size. Early aerodynamic models failed to explain it, but more advanced fluid dynamics eventually revealed that bees don't glide. They paddle through the air with unsteady vortex creation. It's like they stir the atmosphere hard enough to levitate. Honestly, it's both absurd and brilliant. The point is, lift isn't a single clean equation. It's a phenomenon shaped by dozens of interacting variables. Angle, shape, airspeed, pressure, altitude, humidity, they all come into play. And because air is constantly shifting, lift is never a guarantee. It's a negotiation, one you re-sign every second you're in the sky. And for every textbook perfect takeoff, there are still weird outliers, like the time in 1907 when a French inventor built a flying bicycle with flapping wings powered by pedals. It managed to lift a few inches off the ground for a few seconds before collapsing, dramatically and predictably. But the dream was there. The lift, however fleeting, was real. So the next time you feel that rising sensation, the gentle tug of ascent, the moment your stomach flutters as wheels leave the earth, know that you're experiencing one of nature's most complex and beautiful interactions. Lift doesn't just carry metal through the sky, it carries dreams, it carries memories, it carries the hope that maybe, just maybe, we've figured out how to work with the sky instead of constantly falling through it. You're pressing forward now, the nose tilting, gently into the wind, and something deep in the belly of the aircraft growls with purpose. That's thrust, the pushy one, the impatient older sibling of the four forces. Lift might be the graceful ballerina, but thrust is the one in steel-toed boots revving a motorcycle. It doesn't just want to move you forward, it insists. It makes things go and then makes them go faster. You think about how odd it is to fly by pushing. When you drive a car, the tyres grip the road and roll you forward. On a boat, the propeller churns the water behind. But in the air, there's nothing to push against, at least nothing you can see. And yet, here we are, 30,000 feet above the ground, being shoved forward by controlled explosions, invisible spirals of air, or, in the case of some old-timers, a wildly ambitious rubber band. Thrust can come from a lot of places, but it always follows one rule, Newton's third law. For every action, there's an equal and opposite reaction. If you chuck something backwards with enough force, say, a whole bunch of hot gases, then you'll move forward. That's thrust. It's like being flung from a really judgmental slingshot. In propeller-driven planes, thrust is generated by spinning blades that bite into the air and hurl it backwards. You've seen those classic spinning discs at the front of small aircraft or vintage warbirds. They slice the sky, turning fuel into forward motion. The faster the air gets pushed back, the harder the plane moves ahead. It's simple in theory, if not in practice. Each propeller blade is shaped like a tiny wing, an airfoil designed to generate lift in a sideways direction. The lift of the blade becomes thrust for the plane. Aerodynamics, like your taxes, is just confusing enough to make your brain sweat. Now jet engines, they're a different beast entirely. Inside that shiny tube under the wing, there's an orchestra of madness. Air gets sucked in at the front, squeezed by a compressor, mixed with fuel, and then ignited in a combustion chamber. The result? Hot, high-speed gas exploding out the back, pushing the aircraft forward. It's loud, violent, and utterly beautiful. The first true jet engine was designed in the 1930s, independently by two brilliant but underappreciated minds, Frank Whittle in Britain and Hans von Ohain in Germany. Historians still argue which of them deserves more credit. Whittle filed his patent first, but von Ohain got his version airborne first. Either way, jets changed everything. They made it possible to fly faster than the speed of sound, cross oceans without stopping, and build planes so powerful they could outclimb gravity's grip in seconds. Of course, once we could go fast, we wanted to go faster. Supersonic flight brought in afterburners, massive fuel dumps into the hot exhaust stream that create a huge increase in thrust. That's right, you light more fire after the fire. The Concorde, that gorgeous flying dart of the 20th century, used afterburners, to push past Mach 1, but they were loud, thirsty, and only good for very specific situations. Most commercial jets today rely on turbofans, basically jet engines with big fans on the front to move more air with less drama. More efficient, less fun. Still, thrust isn't always about fire and fury. In the early 20th century, one French aviation enthusiast experimented with compressed air-powered flight, creating a small aircraft that puffed along like a glorified hairdryer. It didn't go far, but it did go, which is more than can be said for most of his competitors. Then there's the ornithopter, the mythical flapping wing machine people tried to build for centuries. Some versions relied on pedal-powered flaps, human-powered thrust that made brave volunteers flap like deranged ducks. Spoiler, it didn't work well. But it makes for excellent YouTube rabbit holes. And here's a real fringe gem. In the 1960s, a few experimentalists explored ion propulsion for atmospheric flight. That's right. Thrust without moving parts. Electrodes accelerated charged particles, pushing air molecules in a gentle stream. The technology works, barely, but it's whisper quiet and weirdly beautiful. More suited to space probes, but the dream of silent, frictionless flight still lives. Thrust also behaves differently depending on altitude and air density. Jet engines love the thin, cold air at cruising altitude. Propellers? Not so much. That's why you don't see a lot of biplanes cruising at 35,000 feet. In thinner air, there's less oxygen for combustion and fewer molecules to push against, so engines have to work harder, burn more fuel, and pray that you packed light. One of the strangest things about thrust is how it affects time, or at least our perception of it. The faster you go, the more distances shrink. A flight that once took days becomes hours, and when you approach the speed of sound, things start to get weird. Shockwaves form. The air compresses violently in front of the aircraft. For decades, scientists believed this sound barrier was unbreakable. It wasn't until Chuck Yeager, strapped into the bullet-shaped Bell X-1 in 1947, punched through it with a rocket engine and a grin that we realised the sky had one less excuse to hold us back. Thrust is also what gives planes their personality. A Cessna putters along with a gentle hum, like a lawnmower having a good day. A fighter jet shrieks through the atmosphere like a banshee late for a concert, and the space shuttle, that wasn't flight so much as controlled violence, riding a wave of thrust so powerful it shook windows hundreds of miles away. It's no coincidence we call it liftoff, and not rise gently. Even birds understand thrust in their own way. They push air backwards with every flap, generating just enough forward motion to stay ahead of drag and gravity. Hummingbirds beat their wings so fast they hover. Falcons dive with folded wings, using gravity as bonus. Thrust. Penguins? Well, penguins gave up entirely and went aquatic. Can't blame them. Ultimately, thrust is what keeps you from stalling in mid-air. It doesn't just move you forward, it maintains your airflow, keeps lift alive, keeps drag in check. Lose thrust, and suddenly you're gliding. Glide too long without another push, and you're not gliding anymore, you're plummeting. That's why pilots love their engines the way medieval sailors loved wind. So next time you feel that pull forward as the plane accelerates down the runway, remember, that's thrust at work. It's the unsentimental, slightly reckless partner in this delicate flight equation. It doesn't ask permission, it doesn't care about elegance, it only cares about momentum. And in the grand scheme of things, that's what keeps you soaring through the sky instead of falling back to earth with style. You're up here now, comfortably cruising through that lazy river of sky, but something's still tugging at you, literally. It's drag, that invisible clingy ex who just won't let go. Drag is the sky's reluctance, the atmospheric equivalent of someone standing in the hallway, blocking your exit, asking if you really need to go this fast. And no matter how powerful your engines are, how sleek your wings look, or how optimistic your travel plans may be, drag is always whispering, slow down. So what is drag, exactly? At its simplest, it's resistance. Every time you move through air, you're bumping into molecules, millions of them, crowded together in a giant invisible soup. These molecules don't move politely aside, they push back. Some of them slap into your wings, others curl around your fuselage and create tiny whirlpools of turbulence. All of them are inconvenient. Drag is like trying to sprint through a swimming pool. The faster you go, the harder it gets. There are a few flavours of drag, because of course there are. First, there's form drag, the resistance caused by the shape of the object moving through the air. A boxy shape creates more drag than a smooth one, which is why planes don't look like refrigerators. Even tiny changes in shape can make a huge difference in drag. Engineers obsess over wingtip curves and fuselage tapers like they're sculpting marble, and in a way they are, just with airflow instead of chisel marks. Then there's skin friction drag, which sounds like a weird lotion commercial but is actually very important. It's caused by the air molecules rubbing against the surface of the plane. Even the smoothest looking aircraft has tiny imperfections, microscopic bumps, rivets, seams. All of those catch air and add resistance. That's why airplanes are polished to an obsessive degree, and why early aviation pioneers tried coating their wings with everything from silk to oiled paper. One poor soul even experimented with covering his glider in eel skin, convinced it would slip through the air better. Historians still argue whether it helped or just smelled terrible. Next up, induced drag, which sounds made up but is very real. It's the price you pay for generating lift. As air flows over the wing, it creates pressure differences, and with those differences come swirling vortices, especially near the wingtips. These little spirals of wasted energy trail behind the aircraft like ghostly fingerprints, sapping your efficiency. Modern planes combat this with winglets, those elegant upward flicks at the ends of the wings. They look like fashion accessories but serve a vital purpose. They disrupt vortex formation and reduce induced drag. Bonus, they also look really cool. And then there's wave drag, which only shows up when you're flirting with supersonic speeds. Once you approach the speed of sound, the air doesn't have time to get out of your way. It piles up into shock waves, dramatic and unhelpful, that buffet the plane and slam on the aerodynamic brakes. That's why supersonic aircraft like the Concorde have such slender, needle-like noses. The idea is to slice through the sound barrier, not belly flop into it. You glance out your imaginary window, watching contrails drift lazily behind the engines. Those white streaks aren't drag themselves, but they're evidence of the drama happening in your wake. Hot, humid air from the engines mixes with the cold upper atmosphere, condensing into visible trails. They're beautiful, sure, but they're also a reminder. You're leaving turbulence behind you, whether you see it or not. Of course, drag isn't all bad. In fact, sometimes you want it. Without drag, you'd never stop. There'd be no way to land safely. Pilots use air brakes, spoilers, and even speed brakes, small panels that pop out into the airstream to increase drag when descending. Parachutes work on the same principle, maximising drag to slow descent. And if you've ever stuck your hand out a car window and felt the pressure pushing against it, you've felt drag's strength in its purest, most tactile form. Nature, as always, figured all this out first. Birds are masters of drag management. Swallows have narrow wings and forked tails to reduce drag during high-speed dives. Albatrosses use soaring techniques to exploit wind currents and glide with minimal resistance. Even bugs get in on the act. Dragonflies adjust their wing beat timing to manipulate airflows, reducing drag and boosting lift. Meanwhile, some aquatic birds like puffins have evolved to fly underwater, where the drag is greater, but the physics are surprisingly similar. Engineers have tried to mimic these strategies in aircraft design. The B-2 Spirit stealth bomber, for example, uses a flying wing design to reduce form drag. Its entire body acts as a lifting surface, eliminating traditional fuselage wings tail architecture. It looks like it came from a sci-fi movie, and flies like it borrowed tricks from bats. There's even talk of using active flow control, tiny jets of air or movable surfaces that adjust airflow in real time, reducing drag on the fly, literally. But drag has a sense of humour too. Take the early jet age, when designers thought more speed was the only goal. They built sleek, powerful planes with engines that screamed through the skies, only to find that small changes in airflow created more drag than expected. In one famous case, the addition of an air scoop actually caused such intense shockwave-induced drag that the aircraft struggled to reach its intended speed. Engineers were forced to rethink not just shapes, but why certain shapes behaved the way they did. One quirky historical footnote: in the 1920s Germany, a pilot named Alexander Lippisch flew a glider with no tail and a delta wing, designed to reduce drag and improve manoeuvrability. It looked like a paper airplane drawn by someone with a mild fever, but it flew surprisingly well. His designs later influenced everything from the Concorde to modern spaceplanes. Sometimes weird equals genius. Sometimes it just crashes spectacularly. Aviation history is full of both. What makes drag fascinating is that it's both predictable and mysterious. We have equations, models, wind tunnels, and computational fluid dynamics, but every new design still comes with surprises. A slight miscalculation, a misplaced antenna, even a forgotten piece of tape can affect drag. There's a reason engineers sleep with one eye open during wind tunnel testing. So, as you hum forward through this high-altitude air, remember, drag is always there. Not trying to ruin your day, necessarily, just keeping things honest. It's the price you pay for motion, the tether that stops you from flying off into space, and while engineers and pilots work hard to reduce it, in the end, drag is a reminder that even up here, floating above the clouds, the sky is never really giving you a free ride. Your wings stretch out beside you now, motionless yet utterly alive. They don't flap or flex, not visibly at least, but make no mistake, they are doing everything. They are your sails, your scaffolding, your shield against gravity's grip. And they are weird. Intentionally, beautifully weird. Wings aren't just slapped onto planes for aesthetics. Their every curve, contour, and angle is a deliberate choice, engineered to manipulate the air with surgical precision. These are not mere appendages. These are instruments of lift, control, and sometimes just showing off. You glance at a typical airplane wing, long, gently curved on top, flatter on the bottom, tapering to a crisp edge. Simple, right? But what you're looking at is the result of centuries of obsession, experiments, and more crashes than polite aviation textbooks care to mention. That curve on the top, called the camber, helps generate lift by speeding up airflow over the wing's upper surface. The longer air path up there means lower pressure, and that pressure difference between top and bottom creates lift. Well, partly. As we've said before, the real story is more complicated, and engineers love that. Early wings weren't quite so elegant. In fact, they were barely wings at all. Flat planks nailed to bicycle frames, often with silk stretched over a wooden skeleton and faith holding the rest together. The Wright brothers' 1903 Flyer had a biplane setup with fabric-covered wings and wooden ribs. Functional, sure, but not pretty. Those wings created enough lift to get off the ground in the Kitty Hawk wind, but they were draggy and flimsy by modern standards. Still, they worked. History rarely insists on perfection the first time around. It wasn't long before designers started playing with shapes. Long wings, short wings, stubby wings, swept wings. Some aircraft, like the World War II era Spitfire, had elegant elliptical wings that reduced drag at the tips. Others, like the F-104 Starfighter, went with wings so short and stubby they looked like stunted airplane arms. Historians still argue whether those needle-winged jets were feats of genius or cautionary tales in how not to build a Sky Javelin. Wing shape isn't just about aesthetics, it directly influences how a plane flies. Longer wings offer better lift and efficiency, especially for gliders or long-range aircraft. Shorter wings tend to reduce drag at high speeds and allow for quicker turns. That's why a fighter jet and a 747 don't share a blueprint. They're solving different problems with different flavours of weird. Then there's the aspect ratio, a term that sounds like it belongs in a film editing suite, but really measures how long a wing is compared to how wide it is. A high aspect ratio, think of a sailplane's wings, means better efficiency and smoother gliding. A low aspect ratio, like on an F-16, means manoeuvrability and speed. One is built to dance on the wind, the other is built to punch through it. Let's not forget the dihedral and anhedral angles, small tilts in the wing's orientation that help with stability. A dihedral angle, where the wings tilt upward slightly from the fuselage, helps keep the plane level in flight. Anhedral, where they tilt downward, makes an aircraft more agile but less stable. It's the difference between a yoga master and a caffeinated gymnast. Both have their place. Birds, as usual, got there first. You watch a gull extend its wings into the wind, adjusting tiny feathers to tweak airflow. Every bend and twist is an aerodynamic decision. Birds shift their wing shape mid-flight to optimize lift or reduce drag depending on what they're doing: gliding, diving, landing. Their wings are flexible, reactive, and covered in sensors. Airplanes aren't there yet, but we're trying. Modern planes do have some tricks. Flaps extend from the wing's trailing edge to increase surface area and curvature during takeoff and landing, allowing for more lift at slower speeds. Slats pop out from the front of the wing, changing airflow to prevent stalls. Some wings even flex subtly during flight. Watch a long-winged airliner like the Boeing 787 from the cabin, and you'll see the tips wobble gently as it rides the air currents. That's not a flaw, it's a feature. And then there's the really weird stuff. Experimental aircraft with forward-swept wings that look like boomerangs gone rogue. Blended wing bodies, where the fuselage and wings are one smooth shape, or even closed-loop wings, rare circular structures like the Steeper Caproni barrel plane from the 1930s, which look like someone tried to fly a donut. It didn't go far, but it definitely went down in the annals of aviation's weirder nights. One fringe example worth pausing for, the Hortense. Two German brothers in the 1930s and 40s who developed flying wings with no tail. Their designs were hauntingly beautiful, pure wing, no fuselage to speak of. One of their aircraft, the Horten Ho 229, was a jet-powered flying wing that inspired some of today's stealth aircraft. It flew, sort of. Not well enough to change the war, but well enough to spook Allied engineers and fuel decades of conspiracy theories. Seriously, just Google Nazi UFO, then maybe ungoogle it and go touch grass. Why does this matter? Because every choice in wing design is a trade-off. More lift might mean more drag, better control might mean more weight. No wing is perfect, it's all compromise. An aircraft is a symphony of aerodynamic deals and counter-deals. You give a little here to get a little there. Engineers spend years in wind tunnels shaving off fractions of a percent in performance, all in service of keeping your metal bird aloft with grace. And here's the most magical part. Once those wings are in motion, they manipulate air to create a force strong enough to lift 100 tons of steel, fuel, passengers, and peanuts. Not by flapping, not by brute strength, just by being shaped right and slicing through the sky with intention. It's not brute force, it's finesse. So the next time you're cruising above the clouds, spare a thought for the wings, not the engines, not the tray table. The wings, the weird, wobbly wonders that hold everything together. Without them, you're not flying. You're falling with very expensive luggage. You tilt the nose of your imaginary aircraft just a little, just enough to feel it. The shift in your stomach, the subtle change in airflow, the creeping realization that everything's about to get more dramatic. Welcome to the angle of attack, a concept that sounds aggressive but is really just about posture, your aircraft's attitude, literally and figuratively. This is where things get delicate, dangerous, and occasionally cinematic. Because as it turns out, how you hold your wings matters almost as much as what they're made of. The angle of attack, or AOA if you want to sound like a pilot, is the angle between the wing and the oncoming airflow. Not the angle between the wing and the ground, mind. That's a common mistake, but the direction of the relative wind. It's a subtle distinction, but in flight, subtlety is everything. Change that angle and you change everything. Lift, drag, stability, and whether your plane continues flying or decides to stop cooperating entirely. You increase the angle of attack when you raise the nose of the plane. That tips the wings so they meet the air more steeply. Up to a point, that's great. More lift is generated, which is handy when you're trying to take off, climb, or slow down without falling out of the sky. But like anything in flight, there's a line you don't cross. Go too far, and you reach the critical angle of attack. Cross that line, and the smooth airflow over your wing breaks down into chaos. Lift vanishes, drag spikes. The plane shudders, you stall. Stalling sounds dramatic, and it can be, but it doesn't mean the engine's cut out or the plane falls from the sky like a cartoon anvil. A stall, in aerodynamic terms, is just the point where the wings stop producing enough lift to counteract weight. It usually starts with a slight buffet, maybe a sudden nose dip, a moment of panic in the cockpit. With proper training, it's entirely recoverable. Without it, well, history is full of cautionary tales. Historians still argue whether the first recognised stall occurred during Otto Lilienthal's final glider flight in 1896. He was experimenting with high angles of attack, banking steeply into the wind, when he suddenly lost lift and crashed. Some say it was a gust. Others blame poor structural design. But the aerodynamic stall was clearly at play. Lilienthal's last words were reportedly, "Sacrifices must be made." Not exactly comforting, but undeniably poetic. You lean back now, picturing that moment of balance just before stall. It's like riding a bike up a hill. You can feel the strain, the extra pull, the invisible hand of physics warning you that momentum is about to shift. Pilots call this edge flying on the backside of the power curve. It's where everything becomes more unstable, and every input matters 10 times more than it should. In fighter jets, that edge is pushed intentionally. Pilots often fly close to the critical angle of attack during tight maneuvers. Some planes, like the F-18, are designed to maintain control at ridiculously high angles thanks to thrust vectoring and fly-by-wire systems. But even with advanced tech, the laws of physics don't bend. Push too hard, and the wings will quit their job. No amount of bravado or Top Gun soundtrack can fix that. Interestingly, birds manage their angle of attack with casual elegance. Watch a hawk come in for a landing. It tips its wings upward dramatically, slowing itself, increasing lift just enough to land gently on a branch. Seagulls adjust their angle instinctively when riding thermals or braking against a headwind. Owls, with their big broad wings, shift the angle delicately to maintain silent, low-speed flight. Nature doesn't call it angle of attack, of course. It just calls it surviving Tuesday. Back in the world of machines, angle of attack sensors are critical. Small vanes or probes mounted on the fuselage detect the airflow direction and send real-time data to the cockpit. If the angle gets too steep, alarms blare. In modern jets, you might hear a robotic voice calmly say, "Angle, angle, pull up," which is both helpful and mildly terrifying. These warnings have saved countless lives, especially when pilots get disoriented in clouds or at night. But sometimes sensors fail, or pilots ignore them. The 2009 Air France Flight 447 crash over the Atlantic involved, among other things, confusion about angle of attack data during a storm. The aircraft entered a stall and wasn't recovered. The investigation sparked changes in training and sensor redundancy, but it remains one of the most sobering examples of how crucial this one angle can be. Invisible, simple, fatal if mishandled. Even small planes aren't immune. Student pilots spend hours learning how to recognize and recover from stalls. Nose down, reduce the angle, regain airflow, level out. It becomes instinct. And yet, every year, accidents happen because someone pulled back just a little too hard or panicked on final approach and forgot that more pitch isn't always more lift. One curious fringe story from the 1950s involves a prototype plane with automatic angle of attack correction that ended up overcorrecting and repeatedly flaring into mid-air stalls. The engineers called it the yo-yo of doom. No one was injured, but the nickname stuck. The plane never went into production. There's something poetic about the angle of attack. It's not about speed or power, but balance. Confidence with caution. Boldness tempered by respect. You want to climb, to tilt into the sky, to defy gravity with flair. But if you overdo it, the sky reminds you who's in charge. It's like asking for a raise too enthusiastically. Admirable, but potentially career-ending. And so every takeoff is a dance of angles. You pull gently on the yoke, raise the nose just enough, and lift into the air without crossing that invisible line. During cruise, the angle flattens, the forces stabilize, and your wings breathe easy. On landing, you raise the nose again, slowing the descent without stalling, always flirting with the edge, never stepping over. You settle into your seat again, imaginary or real, and think about how the smallest tilt of metal can decide your fate. Flight isn't just about thrust or lift, it's about posture, about knowing where the edge is and when not to lean too far over it. You hear the faint whistle of wind above you, and then, without a single flap, you watch a bird rise, effortless, regal, a slow spiral upward, wings outstretched, barely moving, riding the air like it was born with an instruction manual you never got. And in a way, it was, because birds figured out flight long before humans managed to get off the ground without breaking something important. You can almost feel your inner child burning with jealousy. How dare they make it look that easy? Birds aren't just animals with wings, they're evolutionary engineers. Every feather, every tendon, every hollow bone is optimized for flight. While you're busy strapping yourself into padded seats and listening to cabin crew instructions on how to inflate a flotation device you'll hopefully never need, a hawk just tilts its tail feathers and executes a textbook landing on a fence post. No hydraulics, no checklists, no runway. Just pure instinct and million-year-old refinement. You probably already know birds have hollow bones, but let's give that fact a bit more credit. These bones aren't just empty tubes, they're internally reinforced with struts and crossbars, like tiny Gothic cathedrals. Light, strong, and perfectly suited for airborne life. Pair that with a rapid metabolism and a respiratory system that pumps air through their lungs even as they exhale, and you've got a creature that's more flying machine than animal. Engineers are still trying to replicate that level of efficiency without lighting something on fire. But it's the wings that truly steal the show. A bird's wing isn't a static structure. It's a morphing tool of lift, thrust, and control. The leading edge cuts through the air. The primary feathers at the tips adjust individually, allowing fine-tuned control of roll and yaw. And the tail, it's not just decorative. It's a rudder, a speed brake, and sometimes a parachute. Birds don't just fly, they pilot. Take the albatross, for example. With wingspans that can reach over 11 feet, these ocean wanderers glide for hours, days even, without flapping. They ride wind gradients and updrafts, skimming just above the waves in what's called dynamic soaring. It's a dance with the wind, performed with barely a twitch. Some scientists have even tracked albatrosses covering more than 10,000 miles in a single journey. No baggage fees, no in-flight pretzels, just wind and instinct. Then there's the hummingbird, the caffeine-addled exception to almost every rule. Unlike most birds, it can hover in place, fly backward, and dart sideways mid-air. Its wings rotate in a figure-8 pattern, generating lift on both the upstroke and downstroke. The blur you see isn't an illusion. They can beat their wings up to 80 times per second. That's not flight. That's physics in fast forward. And yet, for all their grace, birds also crash. Young fledglings miscalculate, adults fly into windows, migration routes get thrown off by weather or fatigue. Evolution didn't grant birds immunity from error, it just gave them better odds. And you? You got a prefrontal cortex, spreadsheets, and an irrational fear of turbulence. Historians still argue whether humans imitating birds was genius or folly. Early aviators were obsessed with replicating flapping flight. Leonardo da Vinci sketched ornithopters, machines with bird-like wings powered by human pedaling or arm flaps. None of them worked, of course. Not because they weren't clever, but because we aren't birds. Our muscles, bones, and proportions are all wrong for flapping. We're built for walking, maybe some awkward climbing. Definitely not airborne elegance. Still, we kept trying. In 1890, French aviation pioneer Clément Ader built a steam-powered bat-winged aircraft named Éole. It had a wingspan of over 40 feet and, allegedly, flew a short distance before crashing. The flight was uncontrolled, unrepeatable, and generally ignored. But it happened. Probably. Historians are still debating the specifics as they do. Over time, the obsession shifted from imitation to inspiration. We stopped trying to flap and started studying glide. Engineers examined bird wings in wind tunnels, noting how air flowed over curved surfaces, how feathers adjusted to changing speeds. The result? Airfoils, those carefully curved wing shapes that now grace every aircraft in the sky. Modern aeronautics still borrows from birds. Winglets, those upward flicks on airplane wingtips, mimic how birds reduce drag with feather placement. Flexible wing designs are inspired by bird joints. Drones are now being built with morphing wings that mimic the way falcons adjust mid-flight. Even swarming algorithms for autonomous drones are based on bird flocking behaviour. Because nature, quite frankly, figured out a lot of things before we even knew what questions to ask. And then there are bats, mammals, but masters of the sky in their own weird way. Unlike birds, bat wings are made of skin stretched over elongated fingers. It's like flying with jazz hands. Their wings are insanely flexible, allowing for sharp turns, hovering and mid-air braking that would send most birds spinning. Some military drone designs have taken a few cues from bats too, because when you want maximum control in tight spaces, it helps to borrow from something that sleeps upside down. But even with all this biological brilliance around us, we didn't just copy. We translated. We took the principles of flight and adapted them to our own tools: metal, fuel, mathematics. We made rigid wings work, designed engines that didn't need feathers, and built control systems to compensate for the instincts we lack. We fly differently from birds, but not entirely separately. Every plane that leaves the runway is still, in a strange way, echoing a sparrow's morning launch. And yet, envy lingers. Birds don't need checklists or navigation charts. They don't care about fuel prices or gate changes. A swift climbs high into the sky, arcs, glides, and plunges just because it can. There's something in that simplicity that still taunts us, no matter how far we've come. So the next time you see a pigeon hop onto a ledge, puff itself up, and lift off without ceremony, spare a quiet moment of respect. That squat little creature is performing a miracle you had to invent an entire industry for. It just does it with a shrug and maybe a crumb still in its beak. You're floating now, not from wings or thrust, but from something older, simpler. You feel the air warm against your cheeks, rising gently in shimmering waves from the earth below. No noise, no engines, just silence and a slow, upward drift. Welcome to the calm, otherworldly realm of hot air ballooning, where flight trades in its jet-fueled swagger for something closer to a whisper. Here, it's not about speed or control. It's about surrendering to the sky's quiet logic. Hot air rises, and that's enough. Of all the ways humans have taken to the air, this is by far the most elegant and least efficient. A hot air balloon doesn't flap or soar or slice through the atmosphere. It simply floats, because the air inside the balloon is hotter and therefore less dense than the air outside. That temperature difference is all it takes. You're no longer fighting gravity, just politely opting out of it for a while. This principle is known as buoyancy, and it's the same reason boats float on water or helium balloons rise in a birthday party stampede. The physics were described as far back as the 18th century, when Joseph Black and later Joseph Montgolfier began experimenting with heated air. The Montgolfier brothers, yes, actual brothers, because of course aviation history is full of sibling rivalries, launched the first successful manned balloon flight in 1783. The passengers, a sheep, a duck, and a very confused rooster, all survived. Eventually humans followed. Historians still argue whether the Montgolfiers truly understood the science behind their creation, or just stumbled onto something that worked. The story goes that they observed laundry drying over a fire and noticed the fabric puffing upward. From this, they reasoned that fire somehow infused air with levitating powers. Not entirely accurate, but it got the job done. Sometimes you don't need perfect equations, you just need a wool sock and an idea. Modern hot air balloons work much the same way. A large envelope, the technical term for the balloon itself, is filled with air that's heated using a propane burner. As the air warms, it expands and becomes less dense than the cooler air outside, creating an upward force. Pull the burner cord and you rise. Let the air cool and you descend. Want to steer? Good luck. Balloons can't steer in the traditional sense, they drift with the wind. Pilots can navigate by ascending or descending into air currents that flow in slightly different directions. It's less piloting, more persuading. But, oh, what a view. In a balloon, you don't roar over the landscape, you hover above it. You hear birdsong, dogs barking from far below. The burner's brief roar is followed by long moments of stillness, where it feels like you've stepped out of time entirely. There's no cockpit, no fuselage, just a wicker basket and a big canvas bubble carrying you like a leaf on an invisible river. There's something ancient about it. You're not in a machine, really. You're in an idea, a controlled, buoyant moment held together by cloth, fire, and faith. And the ground, for once, feels like the thing moving away. Of course, ballooning has its quirks. Landing is less gentle descent, and more, hope there's no goat in this field. Pilots carry ropes to help slow the basket's final approach, and passengers are often advised to bend their knees slightly before impact. There are no runways, just whatever patch of earth happens to be beneath you when you run out of heat or patience. Sometimes farmers emerge from their homes to find 10 tourists in khakis crashing into their cabbages. It's oddly charming, and most balloonists carry bottles of wine as post-landing peace offerings. And let's not forget the more eccentric chapters in buoyant flight. In the 1980s, Larry Walters, a man with absolutely no aviation training, tied 45 helium-filled weather balloons to a lawn chair, packed a sandwich and a BB gun, and lifted off from his backyard in California. He soared to 15,000 feet. That's 3 miles high. He planned to shoot the balloons one by one to descend, but dropped the gun. He eventually drifted into airspace near LAX and was arrested upon landing. His reasoning? A man can't just sit around. And honestly, fair enough, balloons also played a role in war. During the American Civil War, both the Union and Confederate armies used tethered balloons for reconnaissance. High above the battlefield, balloonists could spot troop movements and direct artillery. The military version of yelling "I see you" from the top of a very flammable tree. Fringe aviation has tried again and again to reinvent ballooning. Hybrid airships, dirigibles, and gas bags of all flavours have taken to the sky, some with grace, others with scandal. The Hindenburg famously turned the dream of passenger airships into a flaming cautionary tale. Yet even now, companies are revisiting high-altitude balloons for space tourism and atmospheric science. There's something irresistible about rising without roaring. Flight in its essence is about defying gravity, but in a balloon, it feels more like making peace with it. You don't punch through the air or outsmart it. You harmonise. You rise because warm air wants to rise, and you just happen to be attached to it. No angle of attack, no thrust vectoring, no trailing edge flaps, just buoyancy and breeze. And despite its gentleness, ballooning still makes your heart skip. The moment the ground pulls away, the basket clears the treetops, and the world unfolds beneath you. That's the magic. It's not adrenaline, it's awe. The realization that you're being held aloft by nothing more than hot air and human curiosity. The same curiosity that sent fire into a paper globe in 1783 and still lifts travellers above vineyards and valleys in the soft light of morning. So if you ever get the chance, go up in one, trade noise for silence, trade speed for serenity, and let the wind decide just this once where you'll land. The breeze stiffens just a bit, and your feet are suddenly running over packed earth, chasing something that tugs upward on a long string. A shape flutters into the sky, bright, simple, dancing. It's a kite. Nothing fancy, just a paper diamond with a wooden frame, but it lifts like it's got secrets. You grip the spool and feel the line tighten, trembling with tension as wind and string perform their age-old tug-of-war. This is flight in its most innocent form, or at least it used to be. Before humanity turned it into a weapon, a symbol, and eventually a stepping stone to powered aviation. You probably don't think of kites as part of serious flight history. They're a beach toy, a childhood memory, maybe an occasional casualty of telephone wires. But make no mistake, kites were humanity's first controlled experience with the sky. Long before engines, rudders, or cockpits, we had kites. They floated, dipped, climbed, and crashed, showing us how wind behaved. More importantly, they showed us that something could stay in the air, not just fall more slowly. China takes the credit for the earliest kites, and rightly so. Records go back over 2,000 years. They were made from silk and bamboo, often shaped like birds or mystical creatures. Philosophers and generals alike took note. Kites were more than decoration. They were data collection tools. Ancient Chinese military strategists reportedly used them to measure distances for tunneling under enemy walls. Want to know how far away the enemy gate is? Fly a kite with a string the same length and see when it hovers right above your target. Genius. Mildly terrifying. Very effective. Fast forward to Japan, Korea, and Polynesia. Cultures that took kite flying into the spiritual and ceremonial realm. Some kites were enormous, requiring dozens of people to launch. Others were used to send prayers into the sky, or as part of elaborate festivals that looked suspiciously like early wind-fueled flash mobs. In Micronesia, kites made from leaves were used to lure fish, tying a baited line to a kite that hovered just above the water. It worked, sometimes. Fish aren't known for their skepticism. Then came the science. In the 1700s, Benjamin Franklin famously flew a kite in a thunderstorm to prove that lightning was a form of electricity. He tied a key to the string, which allegedly sparked when lightning struck. There's debate over whether the experiment actually happened as described, or whether it was exaggerated for dramatic effect, but either way, the image stuck. Franklin, drenched and probably deeply regretting his life choices, became the ultimate icon of weather-related overconfidence. Historians still argue whether Franklin truly survived the full brunt of a lightning strike or just observed electrical charge from a stormy sky. But the principle remains: a kite, in the right hands, and maybe the wrong weather, could reach the upper atmosphere long before balloons or airplanes. It was a humble tethered wing that opened the door to sky science, and then, as humans are wont to do, we militarized it. In the 19th century, kites were used for aerial photography and battlefield observation. Lawrence Hargrave, an Australian inventor, created box kites that generated enough lift to carry a person off the ground. His experiments laid the groundwork for understanding lift and stability in controlled flight. He never built a powered aircraft, but he gave the Wright brothers something to study when they were done fixing bicycles. There's a charming footnote from the American Civil War. Union troops used signal kites to send messages across enemy lines. If you ever picture two soldiers in the middle of a battlefield awkwardly untangling kite string, you're not far off. But not all kite flyers were military men. In 1901, a shy Italian named Guglielmo Marconi used a kite to lift an antenna high enough to transmit the first transatlantic radio signal. That's right. The first message to cross the Atlantic without a physical connection floated on string and air. The sky wasn't just for moving things anymore. It became a bridge for ideas. Kites even influenced powered flight directly. The Wright brothers, before building their first glider, experimented with kite designs to test control surfaces. Rudders, elevators, ailerons, all the finicky moving parts that keep a plane stable, were tested with small-scale kites long before they were attached to anything big enough to break a leg. The kite was the wind tunnel of the backyard era. Even today, the kite lives on in unexpected ways. Paragliders, hang gliders, and ultralights borrow their DNA. NASA has studied kite-based systems for launching payloads and collecting atmospheric data. And in renewable energy circles, some companies are developing enormous tethered wings to generate electricity from high-altitude wind currents. Picture a kite farm the size of a football field, pulling turbines through the sky. It's absurd. It's beautiful. It just might work. Of course, not all kite stories end in glory. There's the occasional human tied to a kite, hoping to fly, only to become an unfortunate parable in the local newspaper. There are kite fights, where razor-sharp string is used to cut down opponents' kites mid-air, still a popular and highly competitive sport in parts of South Asia. There are windless afternoons where your carefully constructed creation flops tragically to the grass, but even those moments carry something timeless, the hope that the sky will answer if you just hold on and wait for the right gust. So the next time you see a child running with a kite, string trailing behind, don't dismiss it as a toy. That's not just fun on a string, it's history in motion. The same principles of lift, tension and control that apply to fighter jets and gliders apply to that paper triangle, fluttering joyfully against the breeze. Flight didn't begin with fanfare or fire. It began with fabric, tension and curiosity. It began with a tug on a line, a sudden lift and a shout of surprise. It began, in other words, with a kite. The wind picks up in gentle gusts, stirring dust across a flat strip of sand in North Carolina. You squint into the horizon, where two brothers in bowler hats are arguing over some chains, a bent propeller, and what looks suspiciously like a glider with trust issues. Welcome to Kill Devil Hills, December 17th, 1903, a date forever burned into aviation history. Here, amid gusty coastal wind and stubborn sand dunes, Orville and Wilbur Wright managed something astonishing. They didn't just build a flying machine, they built one they could control. It wasn't the first flight. Others had already glided. Others had even gotten airborne with the help of balloons or steam. But the Wright brothers achieved the impossible trifecta: sustained, powered, controlled flight. A 12-second hop over 120 feet of beach, and just like that, the world changed. You picture it, the Wright Flyer, delicate as a skeleton, fabric stretched over a wooden frame powered by a 12-horsepower engine they designed themselves. No cockpit, no windows. Orville lying face down on the lower wing, holding onto a crude control stick like a man about to pilot a particularly rebellious ironing board. Wilbur runs alongside. The propellers spin, the machine lurches forward, and then airborne. Not by luck, not by accident, by design. The brilliance wasn't just in the engine or the wings, it was in control. The Wright brothers cracked a problem that had stumped many: how to steer in the air. They used a system called wing warping, twisting the wingtips slightly to control roll. Combined with a movable rudder for yaw and a front elevator for pitch, they created the first practical three-axis control system, the blueprint for all modern aircraft. Historians still argue whether others deserved more credit. German engineer Otto Lilienthal had been gliding for years before the Wrights, though without powered flight. French inventor Clément Ader claimed to have flown a steam-powered aircraft in the 1890s. Though no one's entirely sure what flight meant in his case, it may have been more of an aggressive hop. And Brazilian aviation hero Alberto Santos Dumont made impressive flights just a few years after the Wrights, albeit in full public view and with less secrecy. The debate isn't about who flew first, it's about what counts as a flight that changed the world. But the Wrights had something others didn't: relentless focus. They were meticulous, obsessive, and refreshingly free of ego. Bicycle mechanics by trade, they tested designs using a homemade wind tunnel and measured lift coefficients by hand. They adjusted, rebuilt, and rebalanced their machines with the kind of patience usually reserved for monks or clockmakers. And they didn't stop after one flight. They flew 3 more times that day, with the last reaching 852 feet. On the final landing, a gust flipped and damaged the flyer beyond repair. The point had been made. Their success wasn't flashy. No ticker tape parades, no investors lining up. In fact, much of the scientific community initially ignored or doubted them. They kept to themselves, refining their designs, proving reliability through hundreds of flights over the next several years. It wasn't until a demonstration in France in 1908 that the world sat up and took proper notice. By then, they had turned their flying machine into a controllable, repeatable aircraft. Not a toy, not a stunt, a tool. Back in that first flyer, the engine, built from aluminum to keep the weight down, drove twin pusher propellers via a chain and sprocket system borrowed from their bicycle work. The whole aircraft weighed about 600 pounds, which sounds like nothing until you realise they had to transport it via train and haul it across sand dunes by hand. There were no hangars, no runways, and certainly no pre-flight snack service. Just cold mornings, salty wind, and the occasional sceptical seagull. There's something wonderfully absurd about it all. 2 guys from Dayton, Ohio, with no formal engineering training, beat out entire teams of well-funded inventors because they approached flight not as a spectacle, but as a solvable problem. They didn't try to brute force the sky. They studied it, piece by piece, until the sky relented. And yes, their earliest flights were barely longer than a sneeze, but it was enough. Because after centuries of dreamers, gliders, kite flyers, and disappointed inventors, those few seconds marked a threshold. The age of flight had officially begun, and it was propelled forward not by wings alone, but by control. Control changed everything. Once you can steer, you can correct. Once you can correct, you can improve. Suddenly, flight becomes repeatable, then scalable. Within 10 years, aircraft were being used in combat. Within 50, they were carrying passengers across continents. Within 66, we'd put a man on the moon. And that's the real magic of the Wright brothers. Not just that they flew, but that they dared to fly better each time. They refined the machine. They moved the elevator to the back. They added seats, landing gear, and ailerons. They went from lurching across sand to banking gracefully in the air. They went from a backyard experiment to reshaping human transportation. One small, cheeky fact. Orville Wright lived long enough to witness jet propulsion, spaceflight, and commercial airliners. He died in 1948, the same year Chuck Yeager broke the sound barrier. Imagine living through the first 45 years of powered flight and seeing it go from 120 feet in the sand to Mach 1 in the upper atmosphere. That's like inventing the pencil and then reading a Kindle Fire. So the next time you see an airport, a Boeing logo, or a sleepy person leaning against a gate display, think of Orville and Wilbur. Not in a field of glory, but in the sand, elbow deep in gear chains, arguing gently about torque and balance. Not chasing fame, just chasing a little more lift, because that's where it all started, not with glamour but with grit. With every takeoff, we echo that first trembling hop into the air, straining not just to fly, but to steer. Now buckle up, or more accurately, strap yourself into a narrow, high-performance seat, because Subtle has just left the chat. You're no longer floating on thermals or gliding like a bird. You're being flung through the sky in a metal tube designed to hurtle forward faster than sound itself. Welcome to the era of jets, where thrust becomes thunder, and the laws of physics are more like polite suggestions. The romance of flight has officially been turbocharged. Jet engines don't whisper, they don't hum, they roar. They drink fuel like it's an Olympic sport and spit out power at a scale that borders on absurd. Where propellers nibble at the air, jets devour it. And they do it with a single, almost rude premise. Burn stuff, throw it out the back really fast, and let Newton sort it out. The basic jet engine, known as a turbojet, is beautifully brutal. Air enters the front through an intake and gets compressed by spinning blades. That squeezed air is then mixed with fuel and ignited. The resulting explosion forces hot gas out the back, creating thrust. And this whole violent chain of events happens dozens of times per second, continuously, while the plane flies hundreds of miles per hour. It's like setting off fireworks inside a tube and expecting it to push a building forward, and it does. You can thank Sir Frank Whittle and Hans von Ohain for that. In the 1930s, they independently developed the first jet engines. The world was still limping along with piston engines and fabric-covered wings when these two decided to skip a few steps and bring us into the future. Historians still argue over whose design was more efficient. Whittle filed his patent first, but von Ohain's engine was the first to take to the sky in 1939. Either way, the race was on. And soon, the sky wasn't just filled, it was pierced. The Germans unveiled the world's first operational jet fighter, the Messerschmitt Me 262, during World War II. It was faster than anything else in the air, but arrived too late to change the outcome. Still, the future was clear. Jets were no longer theoretical, they were terrifyingly real. The days of canvas-covered biplanes dogfighting over trenches were over. Now, it was all speed, altitude, and unrelenting engine noise. After the war, jet technology exploded. Thankfully, not literally, most of the time. Commercial airliners got faster, sleeker, and higher flying. The iconic Boeing 707 took to the skies in the late 1950s, making international air travel accessible to the growing middle class. Suddenly, the world felt smaller. A journey that once took days by sea could now be made in hours with a few small bags of peanuts and an ill-fitting neck pillow. But of course, faster wasn't fast enough. Enter the Concorde, the crown jewel of supersonic commercial flight. Developed jointly by the British and French, this delta-winged beauty could cruise at over Mach 2, more than twice the speed of sound. That's New York to London in under 3.5 hours, if you're keeping track. Its Rolls-Royce/Snecma Olympus 593 turbojet engines were basically rocket engines that agreed to tone it down slightly for public use. The Concorde didn't just fly fast, it flew high. At 60,000 feet, passengers could see the curvature of the Earth and the darkness of space creeping in above the atmosphere. The plane left behind double sonic booms as it broke the sound barrier, a thunderclap that rattled windows and made sure everyone within miles knew you were late for brunch in Paris. But all that speed came at a price. The engines were fuel-hungry, maintenance-intensive, and loud enough to violate most noise regulations today. After a tragic crash in 2000 and rising operational costs, the Concorde was retired in 2003. Still, it remains a symbol of what's possible when engineers collectively decide the sky isn't enough. They want to bend time. For military jets, of course, the game didn't stop at Mach 2. The SR-71 Blackbird, designed in the 1960s by the US, still holds the record for the fastest air-breathing manned aircraft. With a top speed of over Mach 3, it could outrun missiles and was often clocked at speeds so high the titanium skin would heat up until it expanded mid-flight. Fun fact, the plane leaked fuel on the ground because the metal panels only sealed properly at cruising temperature. Leaking jet fuel? A feature, not a bug. Jet engines have evolved into several types. Turbofans, used in most commercial jets today, turboprops, ramjets, and even scramjets. Each serves a specific speed range and purpose. Turbofans mix bypass air around the engine core, making them quieter and more efficient. Perfect for long-haul flights full of day-old pasta trays and confused toddlers. Ramjets and scramjets. They don't even have moving parts. They rely on sheer speed to compress incoming air. No slow taxiing for those bad boys. They need to be moving very fast to even function. And the noise. Oh, the noise. If you've ever stood near a jet engine on a runway, you felt it. Not just heard it, felt it. Your ribs vibrate, your ears ring, and the air itself seems to recoil from the force. It's a sound that says, I'm not asking permission. It's majestic. It's terrifying. It's why airports have ear protection rules that nobody ignores. Fringe concepts? Oh, there are. Plenty. Pulse detonation engines which ignite fuel in rhythmic explosions like a drumbeat of controlled chaos. Ion propulsion, which, while not useful in the atmosphere, has potential in space. And then there's Sabre, an air-breathing engine designed to operate like a jet and a rocket, potentially enabling single stage-to-orbit flight. If that sounds like science fiction, well, you're not wrong. But someone's already building a prototype. Meanwhile, birds just shake their heads. Hummingbirds can hover without sonic booms. Falcons can dive at over 200 miles per hour without jet fuel. But can they get you to Tokyo in 13 hours with free headphones and a movie you half watch? Didn't think so. So the next time you board a jetliner, squeeze into seat 34C, and hear the engine spool up like an angry metal dragon, know this: you're riding on the legacy of combustion, compression and chaos. It's not just a flight, it's physics screaming at the top of its lungs, channeling heat into motion and motion into altitude. And as the plane roars down the runway, surging into the sky like it's got somewhere very important to be, take a moment to appreciate the engine. It's not gentle, it's not subtle, but by sheer force of fire and pressure, it lifts you off the ground and doesn't stop pushing until the clouds are far below. You're not moving forward anymore, not in the usual way anyway. Instead, you're hovering, suspended between sky and earth, engine blades slicing the air above your head, in a blurring circle of noise and intention. You're in a helicopter now, gravity's reluctant yo-yo, and if fixed-wing flight is a steady waltz with physics, helicopters are a chaotic, jittery tango, where every move is negotiated in real time, and nothing is ever fully stable. They shouldn't work, and yet, they absolutely do. Let's get one thing out of the way. Helicopters are weird. They look like they're making it up as they go. A big spinning blade on top, a smaller one at the back, and a narrow fuselage that seems entirely too fragile to be held aloft by what amounts to a ceiling fan with ambition. But despite their awkward silhouette, helicopters offer something no airplane can: vertical flight. They don't need runways. They don't glide. They lift, straight up like a magician levitating under a spotlight. At the heart of it all is the rotor system. The main rotor, usually with 2 to 6 blades, acts as both the wing and the engine. Each blade is essentially an airfoil generating lift as it spins. But unlike airplane wings, which move forward through the air, rotor blades spin in a circle to create airflow over themselves. By adjusting the angle at which these blades meet the air, a trick called pitch control, pilots can decide whether the helicopter ascends, descends, or just hovers awkwardly like it forgot where it parked. Now, here's where it gets tricky. The rotor blades aren't just fixed in one position. Their pitch changes, constantly, even during each rotation. This is thanks to a device called the swash plate, which sounds like something you'd find in a pirate ship's kitchen, but is actually a crucial component that allows pilots to control each blade's angle throughout its cycle. This changing pitch is what lets helicopters tilt, move forward, slide sideways, or spin in place. It's not intuitive, it's not easy, and it's certainly not something you'd want to learn without supervision. But what about that little tail rotor? Why is it even there? When the main rotor spins, it creates torque, meaning the helicopter's body wants to spin the other way. That's not a gentle spin either. It's the kind of uncontrolled, pirouetting chaos that ends in lawsuits and fire. So the tail rotor provides anti-torque, a sideways push that cancels out the main rotor's twisting force and keeps the aircraft pointed in one direction. Some helicopters, like the NOTAR, no-tail rotor systems, use a jet of air instead. Others use coaxial rotors, 2 rotors spinning in opposite directions to cancel out each other's torque. It's complicated, it's brilliant, it's a little bit terrifying. Historians still argue whether Leonardo da Vinci's aerial screw sketch in the 1480s counts as the first helicopter concept. It was a spiral-shaped device meant to corkscrew into the air, visionary, if completely non-functional by modern standards. The first practical helicopter didn't lift off until the 20th century, with early pioneers like Paul Cornu and Igor Sikorsky leading the charge. Sikorsky's VS-300 in 1939 is considered the blueprint for modern helicopters, with its single main rotor and tail rotor layout. It wasn't fast, it wasn't pretty, but it worked. And that's the charm of helicopters. They're all about what's possible. Not fast, not far, but precise. Need to lift someone from a mountaintop, deliver supplies to a war zone, land on a hospital roof? An airplane would roll its eyes and ask for a runway. A helicopter says, sure. Just give me 5 seconds and some moderately cooperative weather. Military use quickly followed. Helicopters became vital during the Korean and Vietnam Wars, serving as medevac units, troop transports, and gunships. The Bell UH-1 Iroquois, better known as the Huey, became an icon of jungle warfare and rapid deployment. Its distinctive whoop-whoop-whoop rotor sound has haunted and inspired generations of pilots and filmmakers alike. In civilian life, helicopters do the jobs nobody else wants. Search and rescue in treacherous terrain. Helicopter. Airlifting an injured hiker from a crevasse. Helicopter. Traffic report hovering above LA gridlock at 6 a.m. Helicopter, though that job does require a tolerance for both motion sickness and existential despair. Then there's the Chinook, a double-rotor, tandem-blade monster that looks like someone glued two helicopters together and dared it to fly. It does. Majestically. It can carry tanks, troops, or enough bottled water to hydrate a music festival. Its twin rotors spin in opposite directions, eliminating the need for a tail rotor and making it one of the most powerful and versatile flying machines ever built. Of course, helicopters come with their own brand of chaos. They're notoriously difficult to fly. Pilots have to coordinate both hands and both feet simultaneously, managing pitch, roll, yaw, altitude, and heading, all while possibly dodging birds, buildings, and weather. There's a reason helicopters are sometimes described as a collection of loose parts flying in close formation. And maintenance? Oh, it's intense. Every nut and bolt has to be checked. The stress on rotor blades is immense. Vibration is a constant enemy. There's even a term, retreating blade stall, for a situation where one side of the spinning rotor moves slower relative to the wind, causing uneven lift and potential disaster. It's a textbook example of why helicopters keep engineers up at night. Still, their value is undeniable. In places where fixed-wing aircraft can't go, helicopters thrive. Arctic research, jungle relief, oil rigs in the middle of the ocean, they go where runways fear to tread. And with new technologies, like tilt rotors, electric helicopters, and autonomous flight systems, the humble helicopter continues to evolve. One fringe concept you'll love, gyrodynes. These odd hybrids use powered rotors for takeoff and landing, then switch to forward-facing propulsion in flight. Think, the gyrocopter from Mad Max, but with fewer leather outfits and slightly more FAA approval. It's weird, it's niche, it's very real. So here you are, hovering. Not flying fast or far, but flying exactly where you want to be. And that in the end is what makes helicopters miraculous. They cheat the need for forward momentum, they reject the runway, they say, "I'll go up, thank you very much," and they mean it. Now we leave behind the hum of rotors, the swoosh of wings, and the whisper of wind curling over wingtips. We leave behind the sky entirely. Because once you cross a certain line, the Kármán line, around 100 kilometers or 62 miles above Earth, the rules change. The atmosphere thins to the point of near nothing. The sky stops being blue. Air! There isn't enough of it to even bother with. Welcome to space. And here's the hard truth. This isn't flight anymore. This is falling. Falling very fast. Falling so fast, in fact, that you keep missing the ground. The physics of space travel are closely related to the physics of flight, but only up to a point. Airplanes fly by interacting with the atmosphere. Rockets escape it. While an airplane leans on lift, drag, and thrust to stay airborne, a spacecraft relies on momentum, gravity, and a generous supply of fuel with nowhere to land if something goes wrong. There's no lift up here, no air to shape, just raw Newtonian mechanics and the occasional reminder that Earth is a spinning marble, indifferent to your orbital ambitions. To understand the leap from flight to space, imagine tossing a baseball. It follows a curve and falls to the ground. Throw it harder, it goes farther before falling. Now imagine throwing it so fast that the curve matches the curvature of the Earth. It keeps falling, yes, but the ground keeps curving away beneath it. That's orbit. You're falling around the Earth, forever missing it. Terrifying, elegant, and deeply unfair to those of us who can barely catch a frisbee. Rockets, unlike planes, don't generate lift in the traditional sense. Their engines don't push against the air. They expel exhaust at high speeds in the opposite direction of where they want to go. Thanks to Newton's third law, which at this point deserves its own frequent flyer card, rockets propel themselves forward by hurling mass backward, usually in the form of burning propellant at truly excessive speeds. It's thrust, but with rage, and make no mistake, rockets are inefficient beasts. More than 90% of a rocket's mass at launch is just fuel. The actual payload, the astronauts, satellites, or oddly poetic space telescopes, is a tiny fraction. It's like packing for a weekend getaway with 6 U-Hauls of luggage and 1 backpack of clean socks. but that's what it takes to fight gravity to the point where gravity gives up. Historians still argue whether Konstantin Tsiolkovsky or Robert Goddard deserves more credit for modern rocketry. Tsiolkovsky, a Russian schoolteacher, laid out the theoretical groundwork for spaceflight in the late 19th century. Goddard, an American physicist, turned theory into practice with the first liquid-fueled rocket in 1926. His launch in Auburn, Massachusetts, reached an altitude of 41 feet. Not impressive by today's standards, but in 1926. That was the moonshot of lawn ornament heights. Then, of course, came Wernher von Braun, Sputnik, Mercury, Gemini, Apollo. Space became the new frontier. Not just a place to fly, but a place to go. But here's the irony. Once in orbit, you're not flying at all. You're falling sideways at 17,500 miles per hour, constantly. Every satellite, every crewed mission, even the International Space Station, none of them are staying up in the way a plane does. They're falling around the Earth, perpetually in freefall. If it sounds dizzying, that's because it is. And what happens when you want to come back down? You'd think it would be simple. Just fall back, right? But re-entry is violent. You're slamming back into thicker layers of the atmosphere at hypersonic speeds. The friction compresses air molecules so dramatically that temperatures skyrocket. Literally. Re-entry capsules can reach over 3,000 degrees Fahrenheit. That's enough to melt most metals, toast your marshmallows instantly, and ruin any sense of composure. Heat shields aren't optional. They're the only reason astronauts don't arrive, back on Earth as vapor. Airplanes don't deal with this. They slice gently through air, building up speed incrementally. Rockets, they punch through the sky like someone losing a fight with physics and doubling down anyway. But still, humans keep going up. Not because it's easy, and certainly not because it's practical. We go because there's something out there. Something beyond the reach of wings and rotors. Something that makes every heart beat faster when a launch countdown hits 0. Spaceplanes have tried to bridge the gap. The Space Shuttle was the first, and so far only, operational vehicle that launched like a rocket and landed like a glider. Sort of. It had wings, sure, but they were mostly there to keep it from disintegrating in a death spiral. During re-entry, it coasted through the upper atmosphere with all the grace of a brick in a wind tunnel, only slowing down enough to finally glide onto a runway in California or Florida, preferably not on fire. And now we've got reusable rockets. SpaceX's Falcon 9 comes screaming back to Earth and lands on a barge in the ocean. Vertical takeoff, vertical landing, like a giant mechanical candle throwing itself skyward and then delicately balancing back down. It still boggles the mind, because the physics haven't changed, just the precision, the control, the confidence. Of course, airplanes are still better at one key thing: atmospheric flight. You can't beat their efficiency, range, or elegance within Earth's breathable envelope. They cruise smoothly at 500 miles per hour with full drink service and a disappointing bag of pretzels. Rockets will never do that. They're not designed to linger, they're designed to leave. And yet, they both rely on the same fundamental truths: action and reaction. Energy transformed into motion, mass accelerated. Even in space, you're still subject to inertia, momentum, and the occasional irony, just with more stars. So while flight ends where space begins, they remain connected. Two chapters of the same story. Birds gave way to wings, wings to jets, jets to rockets, and maybe someday rockets to something else entirely. Light sails, gravity drives, hypothetical nonsense waiting to become fact. And in the meantime, we keep falling upward, still climbing, still asking what's next. Not because gravity wants us to, but because we've learned how to argue back. Not with wings anymore, but with flame. You come back down now, gently, or maybe with a thud, depending on how generous gravity's feeling, and land not in a cockpit or control tower, but in the presence of creatures that gave up on flight altogether. You walk alongside penguins waddling across the ice, ostriches pacing through dry savanna, and chickens giving you that blank stare they've perfected. All birds, all feathered, all entirely grounded. Welcome to the curious world of flightless beings, where evolution, not ambition, decided to keep feet on the ground. It feels like a betrayal, doesn't it? You spend hours learning how wings generate lift, how flaps and feathers interact with air, how precision and balance can suspend entire machines in the sky. And then, here comes a kiwi bird, all fluff and no flight, looking at you like none of that matters. But it does, because flightlessness isn't failure, it's adaptation, a slow, deliberate decision carved into DNA that says, you know what? We're good down here. Take the ostrich, the largest living bird on Earth, 2 meters tall, 300 pounds of muscle and fluff, legs like spring-loaded pogo sticks. No chance it's flying, not even a little. Its wings? Decorative, vestigial. Used for balance when running, for courtship displays, and, if it's having a rough day, for menacing tourists. But flight, not on the agenda. Instead, it's optimized for land speed, capable of running over 40 miles per hour. If you've got legs that efficient, wings become kind of optional. Then there's the emperor penguin, nature's best-dressed torpedo. It has wings, sure, but they've morphed into flippers. Designed not for sky, but sea. Penguins fly underwater with the same physics, flapping for thrust, body streamlined for drag reduction, even using buoyancy to adjust altitude. It's flight by different rules, in a denser fluid, and it works. They move through the ocean like feathered rockets, chasing fish and dodging predators in 3 dimensions. If evolution had a sense of humour, it was definitely grinning when it made penguins. You might wonder, why would birds give up flight at all? Isn't it their thing? Well, not always. Flight is expensive. It takes energy, complex anatomy, hollow bones, specialised muscles, and usually a relatively small body mass. For birds in environments where flying doesn't offer much advantage, like predator-free islands or ground-based food sources, it becomes a luxury rather than a necessity. If you don't need to escape or travel far, why keep burning calories lifting yourself off the ground? Flightlessness is, in many cases, a strategic retreat. The dodo of Mauritius, now extinct but famously incapable of flight, evolved in a predator-free paradise with plenty of fruit, no need to migrate, and zero pressure to leave the ground. Of course, when humans arrived, with rats, pigs, and casual cruelty, it was a catastrophic mismatch. Evolution gave the dodo millions of years to adapt. Humans gave it about 80 before it was wiped out. Historians still argue over how quickly the dodo vanished after humans landed on Mauritius. Some say within 30 years. Others suggest populations lingered for a few decades longer, slowly declining. Either way, it's a reminder that flightlessness works great, until your environment changes faster than your biology can keep up. Even the chicken, bless its confused heart, is technically capable of flight, sort of. It can flap into the air, usually just high enough to get over a fence or into a low tree. It's what you'd call a weak flyer, like someone who knows how to swim but mostly just dog paddles with a lot of splash and panic. Domestication made chickens heavier, plumper, and altogether more concerned with breakfast than altitude. Flight just isn't a priority when you're bred for thighs. Insects offer their own twist. While some, like ants and termites, only fly during mating season, others evolve to lose wings entirely. Island beetles often abandon flight because wind makes it risky. Better to crawl and stay put than get blown out to sea. In these cases, flightlessness isn't regression, it's precision. And humans? We've done it too, on purpose. Some aircraft, especially stealth planes, flirt with flightlessness in design, at least in the way we understand lift and shape. The B-2 Spirit bomber, for example, looks like a flattened triangle. No tail, no vertical stabilizers. It doesn't fly the way traditional planes do. It relies on computers constantly adjusting control surfaces to keep it aloft. Without automation, it would drop like a very expensive brick. Technically flying? Yes, but barely. Or consider re-entry vehicles, capsules designed not to fly but to fall well. No wings, no lift, just heat shields and parachutes to bring them back in one piece. These craft don't soar, they survive. And in space missions, survival is more important than aerodynamics. In fact, modern drone design sometimes favours non-flying behaviours. Some drones hover in place like insects, flapping or rotating without ever gaining meaningful altitude. Others use wheels, legs, or even perching mechanisms to rest between flights, conserving power. As flight technology evolves, it turns out the ability to stop flying when needed can be just as important as taking off. One quirky footnote: in 2004, a team of researchers in Japan created a robot modelled after a penguin, designed to fly underwater with the same flipper motion. It wasn't particularly fast or efficient, but it did highlight a growing field: biomimicry, where engineers take notes from flightless creatures and apply their adaptations to new machines. Turns out waddling and gliding can teach you just as much as soaring. So you walk through this grounded zoo of evolutionary choices and marvel at the diversity. From cassowaries with taloned feet that could eviscerate a bowling ball, to the kiwi with its absurdly long beak and absolute refusal to be aerodynamic, each of them made peace with the ground. Not through failure, but through refinement. Flightlessness doesn't mean defeat. It means that nature, when left to her own devices, builds what works, not what dazzles. Wings, it turns out, are just one option in a vast menu of mobility, and sometimes the best flight is simply choosing not to fly. And as you stretch your legs on solid ground, maybe for the first time in a while you realise that staying grounded isn't always a limitation. Sometimes it's a strategy. You're cruising comfortably at 36,000 feet when something flickers on the overhead lights. A subtle lurch, a strange vibration underfoot. The engines stutter just for a moment, and suddenly you're reminded that flight, no matter how routine it feels, is still a performance. And sometimes, the laws of physics have notes. Welcome to the sobering reality of crashes, when control slips, systems fail, and gravity, always patient, always waiting, cashes in. Let's be clear, flying is incredibly safe. Statistically, safer than driving, safer than crossing a street while scrolling your phone, and certainly safer than attempting to assemble IKEA furniture without supervision. But safety doesn't mean immunity. Planes crash. Not often, but memorably. And when they do, it's rarely about one big mistake. It's usually a cascading series of small ones, stacking like Jenga blocks until the whole tower tips over. Start with physics. Aircraft, for all their grace, are finely tuned machines balancing four forces in constant tension. Disrupt that balance, say by losing thrust, exceeding stall angle, or hitting turbulence beyond design limits, and things unravel fast. Pilots train obsessively to handle these moments. Simulators mimic disasters so real they can raise your blood pressure just watching. But in the real world, variables multiply. Weather shifts, equipment fails. Human decisions tilt in the wrong direction. One of the clearest examples of how physics wins in a crash is stalling. Not the kind where the engine gives up, but aerodynamic stall. You remember this. Angle of attack exceeds the critical threshold, lift disappears, and suddenly the aircraft isn't flying, it's dropping. If it happens close to the ground, there's no time to recover. If it happens at altitude, recovery depends on altitude, speed, and reaction time. And sometimes, just plain luck. A classic case. Air France Flight 447-2009. A modern Airbus A330 en route from Rio to Paris disappears over the Atlantic. It takes days to find wreckage and years to fully understand what happened. The short version? Icing conditions disabled the pitot tubes, tiny sensors that measure airspeed. The autopilot disengaged. The pilots, unsure of their true speed, pulled back instead of levelling out. The plane entered a stall from 38,000 feet and remained in that state all the way down. No lift, no recovery, just falling. The worst part? The engines were functioning, the wings were intact, the physics were still in the room, but the inputs were wrong. Historians still debate whether this was a training failure, a design flaw in the sensor system, or a tragic convergence of poor visibility and human confusion. The result remains the same, a perfect aircraft lost to imperfect understanding. Crashes also expose one of flight's invisible players, weather. Thunderstorms, wind shear, icing, and microbursts can ruin even the best-laid flight plan. Microbursts in particular are sneaky killers, sudden downward gusts of wind that slam into planes during approach or departure. They push the aircraft toward the ground at terrifying speed, leaving little time to react. Dallas, 1985. Delta Flight 191 meets a microburst just before landing. The jet hits the ground short of the runway and breaks apart. Physics, again, showing its teeth. And then there's mechanical failure. The complex dance of hydraulics, electronics, and metallurgy inside a modern aircraft is remarkably reliable, but not infallible. In 1989, United Flight 232 suffered a catastrophic engine failure that severed all three hydraulic systems, rendering the plane nearly uncontrollable. But the pilots, working with a flight instructor who happened to be on board, managed to guide the crippled plane to a crash landing in Sioux City, Iowa. The aircraft cartwheeled and broke apart. Miraculously, more than half the passengers survived, not because the system worked, because the humans outwitted the failure, at least partially. Sometimes the cause is more disturbing, design flaws that go unnoticed until disaster strikes. The Boeing 737 MAX crashes in 2018 and 2019 exposed a critical issue with the MCAS automated system, intended to prevent stalls but prone to misreading sensor data and forcing the nose down repeatedly. Pilots weren't fully informed, procedures were unclear. The result, 346 lives lost across 2 crashes, all because of a single system asserting itself inappropriately. Once again, physics wasn't the enemy, miscommunication was. But crashes aren't always catastrophic. In fact, many accidents happen on the ground, or during the lowest phases of flight. Birds strike engines, landing gear collapses, runways are overshot. But not every incident ends in tragedy. Consider US Airways Flight 1549, the so-called Miracle on the Hudson. A flock of geese disables both engines shortly after takeoff. Captain Chesley Sully Sullenberger glides the powerless Airbus into the Hudson River with textbook calm. Not a single life lost. Why? Not luck, training, physics, and a pilot who knew how to read the sky in silence. There's a fringe story you'll appreciate. In 1956, a British test pilot ejected from a supersonic jet just as it began spiralling out of control. His parachute didn't deploy properly. He fell from 18,000 feet and crashed through pine trees into a snowbank. Alive. A fluke of trajectory, foliage, and deep snow saved him. The odds were astronomical. His survival, a rare moment when gravity blinked. Crashes also bring about innovation. Every accident, tragic as it is, becomes data. Flight recorders, those famously indestructible black boxes, collect every detail. Engine speeds, control inputs, cockpit conversations. Investigators pore over them for months, reconstructing every second. From that come new regulations, new training, new designs. Each improvement is bought painfully with hard-earned knowledge. Cabins become stronger. Seats are now designed to absorb impact. Emergency slides are faster, more reliable. Pilots receive deeper training on rare scenarios. Cockpit automation grows smarter, but also more transparent, with protocols designed to keep the human in command. Out of the ashes, flight becomes safer, not perfectly safe, but safer. So why do we still fly? Because flight is worth the risk. Every time you buckle your seatbelt and watch the cabin crew mime safety instructions, you're entering a system designed by generations of trial, error, tragedy, and triumph. The jet that carries you is smarter, stronger, and more resilient than its ancestors, not because we got lucky, but because we learned. Flight at its core is physics tamed by persistence. But when it fails, we're reminded that nature never fully lets us off the hook. Lift can vanish, thrust can falter, drag can overwhelm. Gravity will wait, and yet we keep climbing. The engines are quieter now, not because they're working less, but because they're working smarter. Out on the bleeding edge of aeronautics, there's a new generation of aircraft rising. Machines that whisper through the sky, sip energy instead of guzzling it, and flap, tilt, or glide in ways that would have made early aviation pioneers spit out their tea. This is the future of flight, where science fiction edges into science fact, and the sky starts to look different. You're probably picturing a sleek, all-electric aircraft slicing through clouds on battery power alone. Good, that's happening. In fact, it's already here. Electric flight, once a fringe experiment confined to backyard drone nerds and university projects, is now a legitimate industry. Companies around the world, from startups to legacy manufacturers, are racing to develop eVTOLs, electric vertical takeoff and landing vehicles, small, quiet, emission-free aircraft that could one day serve as airborne taxis. Blade Runner vibes, but with less neon and hopefully better customer service. These eVTOLs use multiple rotors, like scaled-up drones, with computers constantly adjusting each one for balance and direction. They hover, ascend, transition to forward flight, and land, all without a runway. Some use tilt rotors, where propellers tilt forward in flight. Others have fixed wings and retractable rotors. It's an entire category of aircraft built around convenience, low noise, and urban mobility. You won't see one doing barrel rolls over an airshow, but you might hail one to skip traffic in 20 years, or maybe sooner. Test flights are already happening. The noise, minimal, the carbon footprint, almost non-existent, assuming the grid powering them is clean. The challenge, as always, is battery technology. You need high energy density, long lifespan, and minimal weight, all inside a power pack that won't catch fire during turbulence. We're not there yet, but we're close enough that people are designing skyports for future commutes. Somewhere, a city planner is trying to figure out how to put a helipad next to a food truck court. But it's not just about small commuter craft. Even commercial aviation is exploring hybrid electric systems. Planes that use electric motors for takeoff and climb when energy demands are highest, before switching to traditional jet engines for cruising. This approach reduces fuel burn, emissions, and operating costs. The dream, a regional airliner powered entirely by batteries or hydrogen fuel cells, cruising quietly over mountains and cities without a trail of CO2 behind it. One fringe idea gaining traction: solar-powered aircraft. The Solar Impulse project proved the concept when it flew around the world using nothing but sunlight. Slow, yes. Quiet, uncannily so. The wingspan was as long as a 747, but the plane weighed less than a family car. It cruised gently, silently, above the clouds, powered by thousands of photovoltaic cells. Not the future of commercial aviation, perhaps, but a glimpse of what sustained, renewable, long-endurance flight could become for science missions, communications, and environmental monitoring. Then there are the morphing wing drones, inspired by birds, bats, and bugs. These small aircraft have flexible wings that change shape mid-flight, just like a bird tucking its wingtips or spreading its feathers. Researchers are experimenting with materials that bend and twist like muscle and bone, not hinges and rivets. The result? Drones that can hover, dive, glide, and shift posture for precision or stealth. Not only more efficient, but eerily lifelike. Even the physics of how we fly are being questioned. Conventional wing and fuselage designs are being challenged by blended wing bodies, where the entire aircraft acts as one massive airfoil. No separate tail, no narrow tube with wings glued on, just a wide, gently curving body that produces lift across its entire surface. The payoff? Drastically reduced drag, greater fuel efficiency, and more usable cabin space. The kind of plane that looks like it belongs in a sci-fi movie, because until recently it did. You'll appreciate this one: ion propulsion for atmospheric flight. Normally confined to satellites, ion engines use electric fields to accelerate charged particles, creating a whisper of thrust. Too weak for heavy loads or high speeds for now, but recent tests have demonstrated ion-powered gliders that float without moving parts. No combustion, no noise, just fields and ions. It's slow, silent, and a bit eerie, like watching a ghost hover by. Historians may someday debate when the second age of aviation began. Was it the moment we electrified flight? The moment drones became self-flying delivery bots? Or when hydrogen-powered aircraft quietly crossed the Atlantic without a drop of fossil fuel? Each of these represents a shift, not just in how we fly, but why. The next century of aviation is as much about sustainability and access as it is about speed or altitude. And here's where things really get wild. Concepts like anti-gravity propulsion and reactionless drives still lurk in the corners of speculative science. No evidence, no working prototypes, but they persist, like whispered rumours in hangars late at night. Even if they're never real, the fact that humans are still dreaming that big says something about us. We didn't stop wondering what comes after wings. Then there's space tourism, inching closer to commercial reality. Not spaceflight as escape velocity and orbit, but suborbital hops. Blue Origin and Virgin Galactic are sending civilians to the edge of space in vehicles that blur the line between rocket and plane. It's a new kind of flight, one that arcs into space just long enough to see the curve of the Earth, then coasts back down on ballistic trajectories. Costly, yes. Controversial, definitely. But undeniably flight, just with a different script. And back on Earth, birds continue doing their thing. No batteries, no apps, no carbon offsets. Just feathers, instinct, and 100 million years of practice. So what's next? Smarter flight, cleaner propulsion, autonomy that doesn't just avoid obstacles but thinks, craft that learn from nature, adapt in real time, and interact with weather, terrain, and other aircraft like a flock rather than a formation. You might not even notice them anymore. quiet, smooth and efficient, the air filled with motion too subtle to fear. The sky is still there, but it's changing, and so are we. The sun has set now, and the sky darkens to that familiar inky blue, a canvas not just for science, but for story. Because long before we understood airflow and angles of attack, before wind tunnels or winglets, we looked up and imagined. We dreamed of rising, not with rivets and rockets, but with wax wings, broomsticks, thunderbirds, and divine chariots. The history of flight doesn't begin with engines. It begins with myth, magic, and a generous amount of hubris. Welcome to the unscientific sky, where physics takes a nap and fantasy takes the controls. You've heard the story of Icarus, of course, Daedalus' son, imprisoned in the labyrinth, crafting wings from feathers and wax to escape. It's one of humanity's earliest flying daydreams, and like most myths, it ends in disaster. Icarus ignores his father's advice, flies too close to the sun, and falls into the sea when his wings melt. The message? Don't get cocky. Or maybe, make better adhesives. But really it's a tale of ambition, the desire to rise above, even when gravity has other plans. Greek mythology wasn't alone. The Hindu epic Ramayana features the Pushpaka Vimana, a flying chariot gifted by the gods. Described in vivid detail, it could travel at incredible speed and respond to thought commands. Scholars still debate whether these texts reflect symbolic storytelling, ancient science fiction, or, depending on who you ask on the internet, evidence of alien visitors with excellent taste in interior design. Over in China, legends told of flying dragons, serpentine creatures that soared through the heavens, associated with rain, storms, and imperial power. Flight was not just movement, it was divinity. To fly was to rise above the human condition, to approach the realm of gods, spirits, and sky beasts. No wonder emperors liked the imagery. Meanwhile, Norse mythology gave us Valkyries, warrior maidens who flew across battlefields, choosing who would live and who would die. Their winged helmets and sweeping capes echoed the drama of airborne supremacy, though it's unclear if they dealt with turbulence or the occasional cabin pressure warning. Then there's Pegasus, the winged horse, born of blood and legend, galloping through the sky with poetic inefficiency. Witches too took to the air, though not always willingly. In the Middle Ages, it was widely believed, or at least widely accused, that witches could fly using enchanted broomsticks, often after rubbing themselves with mysterious flying ointments made from herbs, hallucinogens, or less mentionable substances. Some accounts suggest the sensation of flight may have been the result of psychedelic-induced dreams. Others insist it was real, and naturally involved cats. One particularly quirky account from the 15th century describes a man named Guillaume Edelin, who confessed, under encouragement let's say, to flying through the air after striking a deal with the devil. He described it not as soaring, but as a strange floating, a sort of horizontal levitation. The inquisitors were not amused. Flight back then was a suspicious business. Too much upward movement could get you burned at the stake. In Jewish folklore, there's the tale of Solomon's carpet, a flying mat so vast it could carry his entire army. In Irish mythology, magical cloaks could lift warriors into the air, and let's not forget flying palaces, floating islands and clouds that transported mortals across continents. Flight was never just escape, it was power, transformation, enlightenment, and often punishment. Historians still argue whether these myths were pure imagination or faint echoes of misunderstood technology. Was the Pushpaka Vimana inspired by astronomical observations? Were the witches' flights ritualistic visions tied to seasonal trance states? Or were these just stories to explain what couldn't yet be built? We may never know. But the urge to fly, before it was mechanical, was spiritual. And then there's the madness. In the centuries before the Wright brothers, the skies were filled with hopeful lunatics. In the 17th and 18th centuries, flying men leapt from towers with feathered wings strapped to their arms. Some flapped furiously, others coasted off rooftops, confident that belief would conquer drag. Spoiler, it didn't. One Englishman built an entire flying machine based on the way pigeons fold their wings. It failed, spectacularly. Witnesses claimed he flapped all the way down. Balloon hoaxes were common. In 1835, the New York Sun published a series of articles claiming that an English astronomer had observed bat-winged creatures flying on the moon through a massive telescope. People believed it for a while. The hunger for flight was so deep that even lunar batmen sounded plausible. One lesser-known oddity: in 1897, hundreds of Americans reported seeing mysterious airships hovering silently in the sky. They described cigar-shaped craft with powerful spotlights and mysterious operators. This was before the Wright brothers flew. Newspapers debated whether it was an alien visitation, a secret government test, or mass hysteria. Nobody ever found a ship. Just stories. Glorious, confounding stories. And maybe that's the point. Before we had the math, we had metaphor. Before physics, we had fantasy. We dreamed of flying not because it was practical, but because it was impossible. The stories were our rehearsal. The myths, our design sketches, the flying carpets, broomsticks, and dragon-backed kings. They gave us a sky worth aiming for, even if we didn't yet know what angle of attack was. Even today, those dreams linger. Look at how we talk about flight. Taking off, soaring, rising above. It's never just motion, it's transcendence. Flying is still coded in our language as escape, as freedom, as magic. And every time a rocket ignites or a drone hums overhead, there's still a flicker of awe, a whisper of Icarus, of dragons, of that ancient irrational hope that maybe this time we'll touch the clouds and live to tell about it. So as you stare into the darkened sky, tracing the path of satellites and distant planes, remember, not all flight is measured in thrust and lift. Some of it begins with a story. You step outside and tilt your head up. The night is quiet. Somewhere high above, a jet hums softly, its lights blinking in measured rhythm, barely visible between passing clouds. There's no thunder, no spectacle, just another aircraft tracing its familiar arc across the sky. And in that quiet moment it hits you. The sky was never truly empty. Not in myth, not in biology, not in engineering. It has always been full of movement, of dreams, of strange and stubborn ambition. Flight isn't an invention, it's an inheritance. From beetles to bombers, the air has always been a place we wanted to belong. Every flutter, glide, swoop, and sonic boom is part of the same story. A conversation between gravity and imagination. Even now, as aircraft become quieter, sleeker, more automated, they're still participating in that same defiant act, moving through a medium that was never designed for us. You think back to the insects, beetles with hardened elytra that split open to reveal delicate wings, moths with surface scales that reduce turbulence mid-glide, flies with halteras, those tiny vibrating appendages that act like gyroscopes, keeping them stable through impossible acrobatics. They don't know lift equations, they don't write flight manuals, but they fly perfectly. And the birds, engineered by nature with precision humans still struggle to match. The high aspect ratio of an albatross wing, the variable geometry of a falcon's feathers, the shock-absorbing wrist joint of a bat. The air has always been full of living flyers. Every airplane ever designed is in some way an homage to them, even if it doesn't flap. We built our machines to imitate, then to outperform, and eventually to redefine flight. From biplanes with sputtering engines to composite-skinned, fly-by-wire, stealth-configured aerial marvels, we went from mimicking pigeons to punching holes in the sky. And now, we're folding that ambition into smaller, smarter forms. Drones the size of dragonflies, gliders that harvest solar power, rockets that land themselves backwards on tiny ocean platforms. But the sky hasn't changed. It still resists, still pushes back, still reminds us on occasion that the ground is only ever one mistake away. Every flight is borrowed time, every takeoff is a bet, every landing a handshake with physics. Even autopilot can't fully automate that truth. There's a quiet paradox at the heart of flight. The more we master it, the more invisible it becomes. Airports feel mundane, boarding passes, routine. Most passengers don't think about lift, drag, or fuel ratios. They think about legroom, Wi-Fi, whether there'll be peanuts. And that's part of the miracle too. Flight has become so normal, we forget to be amazed. But it only feels normal because the system underneath it is a masterpiece of layered complexity. Still, the sky isn't just full of aircraft, it's full of stories. Every contrail is a thread between places, Every black speck crossing the sun is someone's first flight. Somewhere out there, a pilot is logging their final hours before retirement, easing the yoke gently as they descend. Somewhere else, a student is gripping the stick for the first time, bouncing along a runway with white knuckles and big dreams. In between, a cargo drone delivers insulin across an island. A balloon rises silently into the stratosphere with a telescope strapped underneath. A glider circles inside a rising thermal. A paraglider hugs a mountain's edge, dancing with the wind. Even the sky itself plays a role. It shapes how we move, when we launch, how we land. It gives us jet streams to surf, thermals to ride, and turbulence to endure. Pilots learn to read it the way sailors read waves. Engineers model it in supercomputers. Weather forecasters chase it in hurricane planes. And sometimes, rarely gloriously, we just sit in it. A balloon drifts. A wingsuit cuts a line through a canyon. A pilot turns off the engine and listens to the silence. Historians still debate what flight means for humanity. Was it the defining innovation of the 20th century, a stepping stone to space, a tool for connection, or a symbol of our relentless need to go faster, higher, farther? The answer, of course, is yes, all of the above, because flight is never just transportation, it's transformation. We don't fly to get somewhere, we fly because we're wired to reach. And not all flight requires leaving the ground. Sometimes a kite lifted by a child's hand is enough. Sometimes it's a dream, a drawing, a design scribbled on the back of a receipt at 2 a.m. The Wright brothers built their dream in a bicycle shop. Amelia Earhart charted hers from a yellow Kinner Airster. Flight doesn't begin on a runway. It begins in the moment someone looks up and says, "What if?" So, you lower your gaze from the stars, take one more breath and feel it. The sky has weight. Not just the molecules of nitrogen and oxygen, but the history that floats in it. It's crowded in the best way possible, full of wings, both feathered and forged, full of people who dared, full of machines that hum with quiet defiance. And you're part of it now. Every time you look up, you're not looking into emptiness, you're looking into possibility, and now you let yourself drift. The sky softens around you, not the roaring, turbulent sky of engines and airspeed, but a quieter, gentler one. A sky that feels like silk drawn slowly across the back of your hand. The kind of sky that holds its breath at dusk and only exhales when the stars begin to show themselves, one shy point of light at a time. You float here for a while, neither climbing nor descending, suspended in the afterglow of everything we've learned. The physics of flight, those intricate equations, those invisible forces, they're still here, but they've loosened their grip a little. Now they're background music instead of marching orders. No more thrust calculations, no lift-to-drag ratios, just a calm, even hum, like the distant murmur of wind over wings. Above, the clouds don't chase you anymore, they welcome you. Below, the earth falls away gently, like it knows you'll come back eventually. For now, you hover in a kind of in-between, a place where time slows and movement becomes suggestion rather than command. Even your thoughts move differently here. They spiral slowly, like the lazy thermals that birds use to stay aloft without flapping. One thought tucks into the next, like feathers smoothing into place. You remember ancient kites pulling against silk strings, rocket engines waking the sky, bees paddling through the air with improbable grace. It all blends together now. Not a timeline, just a warm blur of motion. You feel your breath even out. The cabin lights, if there were any, would be dimmed. A fan whirs softly somewhere, steady as a metronome. Even gravity seems to have stepped back for a while, letting you float weightless in your own imagination. It's okay to let go of the details now. No more stalling speeds, no more fuselage cross-sections, no more whispery tales of wax. Wings, just stillness, just air. You've earned your landing.